Good afternoon, one and all. Welcome to the afternoon session for today. And in this afternoon, we are going to have a first session taken by two eminent speakers. The first one is Dr. Ashok Bogi. Dr. Ashok Bogi has completed his MSc Physics and PhD from Osmania University, Hyderabad. He has qualified TS set in Physical Sciences conducted by Osmania University. He has successfully completed 12 years of service in VNRVJIET, and he has total 17 years of teaching experience. And currently, he is working as an assistant professor of physics and chairman BOS in physics in the Department of Humanities and Sciences. He is also NSS program officer in our college. He has published 30 research papers in various national and international journals and conferences. Most of his papers are indexed in Scopus, Web of Science, and ACR. He also published one patent on his research work. Dr. Ashok Bogi has received several awards. He has received Best Teacher Award by Lions Club of International on 5th September 2021 on Teachers' Day celebration. Received a certificate of Outstanding Researcher in Material Science by World Research Council, and received the certificates of Outstanding Contribution in Reviewing from various journals. Dr. Ashok Bogi is a reviewer for various reputed national and international journals. He is also a member in editorial board of Journal of Physics, Journal of Material Science, and International Journal of Material Science and Applications. He is a life member in Material Research Society of India, MRSI, and Indian Science Congress Association, ICA, and World Research Council. He is also member BOS in Physics in St. Peter Engineering College and KG Reddy Engineering College. With this brief note, I welcome Dr. Ashok Bogi, sir, to give a lecture on characterization of materials on X-ray diffraction, optical, and EPR studies. Thank you, sir.
Thank you, Dr. Pavan Kumar, for introducing me in a nice way. Good afternoon, one and all. This is Dr. Ashok Bogi, working as an assistant professor of physics in the Department of Humanities and Sciences, VNRVJIET. Coming to my presentation, the title of my presentation is Synthesis and the Characterization of Amorphous Materials by XRD, Optical, and EPR Spectroscopy. Outline of my presentation is introduction, experimental, characterization techniques, results and discussions, and conclusions. Coming to introduction, based on the atomic arrangement, the solids are classified into two categories. They are crystalline solids and non-crystalline solids. Here, the non-crystalline solids are also termed as amorphous solids. So, this is the geometrical nature. So based on the atomic arrangement, the solids are classified into two categories. There are crystalline solids and amorphous solids. The amorphous solids are also termed as non-crystalline solids. This is the geometrical nature of crystalline solids. The crystalline solids are the solids in which all the atoms are arranged in the regular manner. So these crystalline solids are having anisotropic in nature and highly symmetrical in nature. Because of highly symmetrical in nature, all the bonds in the crystalline solids are equally strong. As temperature of the given crystalline solid increases, all the bonds will be ruptured at a particular temperature or at a unique temperature. That's why these materials are having a sharp melting point. Coming to the second one, amorphous materials. This is the geometrical representation of amorphous materials. The amorphous materials are the materials in which all the atoms are arranged in irregular manner and the environment about any atom is not same. These materials are having isotropic in nature and highly asymmetrical in nature. Because of highly asymmetrical nature, some of the bonds in these amorphous materials are weakest bonds, some bonds are intermediate bonds, some other bonds are strongest bonds. As the temperature of the given amorphous material increases, the weakest bonds ruptured at lower temperatures, the intermediate bonds will be ruptured at intermediate temperatures, the highest bond, the strongest bond will be ruptured at elevated temperatures or at higher temperatures. Hence, the non-crystalline solids or amorphous solids are having extended melting point. So this is the diagram. By looking at this picture, this is the picture. By looking at this picture, we can understand how the atoms are arranged in the crystalline solids as well as in the amorphous solids or non-crystalline solids. So the studies on amorphous materials also cover various systems like glasses, polymers, thin films, intermetallic materials. But most of the research in amorphous materials is dedicated to glassy materials. So, but what is in the glass material? So, glass is a inorganic product. Glass is an inorganic product of fission which has been cooled to rigid condition without any crystallization. So, glass is a amorphous solid in which the three-dimensional arrangement is absent. Glass formed by rapid melt quenching and annealing. So what is meant by rapid melt quenching and annealing? I will explain in our next slide. So coming to next one, the term glass is often used to describe any amorphous solid that exceeds the glass constant temperature. The short range periodicity is the important characteristic of a amorphous material. These materials possess ionic ionic as well as covalent bonding interaction. According to Zakarian rules, the according to Zakarian rules, the oxides of type AO, A2O does not form the glass structure, but the oxides of type AO2, A2O3, and A2O5 form the good glass structures. Here I have mentioned a few glass formers. All these glass formers are in the form of AO2, A2O3, and A2O5. For example, SiO2 silicate, GeO2 germanate, P2O3 to borate, and phosphate P2O5. So these are the best glass formers, and all these glass formers are in the form of a AO2, A2O3, and A2O5 structures. Next slide. It's not moving. Borate glass among the above. So just now I showed you. So here the best glass formers are silicate, germanate, borate, phosphate. Among the above glass formers, here I am going to concentrate only on the borate glass materials. So here the borate glass is a well-known and best choice as optical material due to its high transparency. Next one, low melting point and high thermal stability. It is generally used for the formation of dielectric and insulating materials. The structure of the borate glasses is mainly composed of BO3 triangles forming six-membered boron ring connected by the BOB linkages. So this is the diagrammatic representation or geometrical representation of the BO3 triangles. So coming to the next line, so here the alkali and alkaline oxides like lithium oxide, sodium oxide, potassium oxide, magnesium oxide, next one calcium oxide, barium oxides are the best network modifiers in the glass network. But what is the use of these network modifiers? So these network modifiers are used to break up the continuous network by creating the non-bridging oxidants at the expense of bridging oxidants. Once the non-bridging oxidants are increased in the glass materials, their indirect band gap will be decreased. When boric acid is incorporated with glass modifiers, its internal structure is rearranged due to formation of non-bridging oxidants. This is the structure of the boron glass materials with modifier oxides due to the incorporation. Due to incorporation of modifier oxides, the internal structure of the internal structure is rearranged due to formation or due to the enhancement of non-bridging oxygens at the expense of bridging oxygens. Once the non-bridging oxygens are increased, the inductive band gap values will be decreased for these glass materials. So recently, much awareness has been paid to research in inorganic glasses doped with transition metal ions because most of the transition metal ions are exist in different oxidation states. For example, if you take copper, which is exist in Cu1 plus and Cu2 plus. If you take manganese, it exists in Cu2 plus and Mn2 plus and Mn3 plus. If you take iron, it exists in Fe3 plus and Fe2 plus, and so on. So because of the different oxidation states, these transition metal ions have paid very much interest in the research field. So, due to these transition metal ions, sorry. So yes, because of the different oxidation states of transition metal ions, so they influence the various properties like physical properties, optical properties, and structural properties. And due to incorporation of the transition metal ions, the applications of boron classes have been enhanced to optoelectronic devices. Here I have mentioned the oxidation states of various transition metal ions. Coming to experimental, so here I have chosen this glass composition. So here in our present study, that is 25 Li2O, 15 SRO, 60 minus X B2O3 X MNO, where X equal to 0, 0.2, 0.4, 0.6, 0.8, and 1 more percentage. So due to the incorporation of MNO transit metal ion, the applications of this boron glass system has been increased to radiation shields, host material for lasers, glass ceramics, and so on. So coming to the glass core and glass sample, so here the first sample is labeled as M0, so in which there is no transit metal ion, so 25 Li2O, 15 SRO, 60 B2O3, and by moving in the downward direction, the transit metal ion percentage has been increased instead of 0.2 more percentage. And all these samples were synthesized by the melt quenching technique. Actually, there are so many techniques to prepare the glass materials, such as the salt gel method, co-precipitation, hydrothermal method, melt quenching technique, and so on. Among the above methods, the conventional melt quenching technique is simple and widely used for the preparation of glass samples because of the following reasons. The first one is so here. If you use the conventional melt quenching technique, so the following advantages are there. The first one is glass preparation and handling are very easy. Speedy preparations of innumerable compositions of glass are possible, and this is very important one. Simultaneously, both amorphous and crystalline nature can be obtained in the same melt. Next one is large flexibility of the composition, flexibility of geometry of glass. Because of these advantages, so here the conventional melt quenching technique is used in the present study, which is very much useful for the preparation of glass materials are amorphous techniques. So here this is the flow chart which gives the various steps to prepare the glass materials. So here these are the starting materials. So manganese oxide, scansion, lithium, boric acid, these are the starting materials. And here this is the muffle furnace, programmable electrical furnace. Next one, this is the crucible, and these are the molds, and this is the again mortar. So the starting materials used in the preparation of glass samples are manganese oxide, strontium oxide, lithium oxide, and boric acid. So here the initially the stoichiometry amounts of chemicals were weighed using digital balance with an accuracy of 0.001 grams and mixed together and grinded to fine powder in an agate. Mixed together and grinded to fine powder in an agate mortar. So this is the agate mortar which can be used to grind the powder. Now we are at the first step for batch preparation. Now the batch preparations were completed. So after getting the fine powder, so the either 5 gram batch or 10 gram batch mixture was taken. Mixture was taken in a porcelain crucible and kept in a programmable electrical furnace and raised the and increased the temperature up to desired temperature. So here, as temperature increase at a particular stage, we'll get the melt. So here, while getting the melt, the melt is chilled frequently to ensure the homogeneity nature. And next one, so after getting the melt, so the melt was quenched by pouring on the steel mold plate, maintained at 100 degrees centigrade, and immediately pressed with another steel plate, so to obtain the transparent glasses. Now the transparent glass materials are obtained. After obtaining the transparent glass materials, immediately those materials are shifted to another programmable electrical furnace maintained at 300 degrees centigrade for annealing purpose. So in order to remove the stains in the glass materials. So coming to the characterization techniques, so under characterization techniques, I am going to explain the XRD UV visible optical absorption electron parameter resonance spectra of the prepared glass samples. In that, the first one is the X-ray diffraction. I think you know. So your X-ray diffraction is a non-destructive technique. Non-destructive technique which can be used to characterize the glass samples or amorphous materials. And this method is used to analyze the internal structure of the sample, and also use it to measure the nature of the sample. Nature of the sample means either maybe so your crystalline nature or amorphous nature. So the in this X-ray diffraction technique, we use the X-rays. We use the X-rays. The X-rays strikes the sample and landed on the detector. This is the X-ray beam. So the X-rays strikes the sample and landed on the detector, produce the scattered beams. Actually, in this X-ray diffraction phenomena, we use the X-rays. So before going to discuss about the working principle of X-ray diffraction, we need to know how the X-rays are generated. So here, how the X-rays are generated. I think we know. So X-rays are generated. X-rays are generated when the fast-moving electron beams are suddenly stopped by a target material. Suddenly stopped by a target material. When the fast-moving electron beam strikes the target material, the kinetic energy of the electron is converted into thermal heat energy as well as X-rays. So here this is the X-ray tube. This is the X-ray tube which can be used to generate the X-ray radiations. In this X-ray tube, so here this is the cathode material. In place of cathode material, we are using the tungsten filament. But here we need to know why we are using the tungsten filament. Why not some other filament? Because the tungsten filament emits or ejects the more number of electrons easily when it is heated to suitable higher temperatures. And next one, this is the so here this is the anode. This is anode. So this is the cathode, and both are connected in the forward bias. When the bias is applied among the cathode and anode, the electrons are generated from the cathode material and are allowed to strike the target anode material or target material. When they strike the target material, the kinetic energy of the electron beam is converted into heat energy, that is thermal energy, and so X-rays. Finally, we get the X-rays. This X-ray tube. So coming to X-ray diffraction and working principle, so XRD works on the principle of branch law and uses monochrome X-rays to analyze the sample. This is the Philips PW 30 X-ray diffractometer, which is there in the department of Physics, Usman University. So here, the next one, these are the internal parts of X-ray diffractometer. So here, this is the first one, X-ray tube. X-ray tube. Next one, this is sample holder. Next one, this is the detector. Actually, beside X-ray tube, we have a goniometer. Beside X-ray tube, we have a goniometer. This goniometer is used to measure the angle between inset radiations and diffracted radiations. Actually, in X-ray diffractometers, there are two types of goniometers. One is theta 2 theta goniometer. Other one is the theta theta goniometer. In the theta 2 theta goniometer, the X-ray tube is at rest position. The sample holder moves by an angle theta, whereas the detector moves by an angle theta. So that's why we use the 2 theta as X parameter while drawing the X-ray diffraction patterns. And coming to second one, theta theta goniometer. In the theta theta goniometer, the sample holder is at rest position. The X-ray tube moves by an angle theta, and the detector also moves by an angle theta. Therefore, the angle between incident beam and the diffracted beam is equal to theta plus theta, which is equal to 2 theta. That's why we use the 2 theta as X parameter while drawing the X-ray diffraction patterns. Next one. So yeah, this is the other diagram. This is other form of the internal structure of the X-ray diffractometer. So here this is the X-ray tube. Next one is the sample holder, and this is the detector. when the X-rays fall on the sample, they interact with the, or when the X-rays fall on the glass sample, every atom of the glass sample diffracts X-ray radiations in all the directions. Out of all those X-ray diffractions, only in certain directions, the excitations are in phase with each other, and in some other directions, the excitations are out of phase with each other, resulting in the development of constructive interference and destructive interferences. These constructive and destructive interferences are used to gather the different information about the sample. So here, these are the incident radiations. These are incident radiations. When these incident excitations fall on the glass sample, different glass sample, so the atoms of glass sample diffract radiations in all the directions. Finally, we may get either constructive interference or destructive interference in this case. So coming to next one. So coming to constructive interference, when will we get the constructive interference and when will we get the destructive interference? So here, when the two rays are in phase with each other, when the two rays are in phase with each other, we get the constructive interference. In the constructive interference case, the crest of the first wave combines with the crest of the second wave, then the resultant amplitude or resultant intensity will be maximum. So here, this constructive interference occurs when the total path difference, and actually these are the incident X-radiations, these are the diffracted X-radiations. The path difference between these two diffracted X-radiations is 2d sin theta. The path difference between these two X-radiations is diffracted X-radiation. Please try to observe. Diffracted X-radiations is 2d sin theta. If this path difference 2d sin theta equal to n lambda, then we obtain the constructive interference. Otherwise, we get the destructive interference. Coming to second one, destructive interference. When the two rays are out of phase with each other, then we will get the destructive interference. In the destructive interference case, the crest of the first wave combines with the curve of the second wave or vice versa, and the resultant amplitude or resultant intensity will become maximum. This destructive interference is occurred only when the path difference between these two diffracted X radiations 2d sin theta is not equal to n lambda r, which is equal to 2n plus r minus 1 into lambda by 2. So these are the two important cases in the Bragg's law. So here, coming to next one, characteristic spectra. When these X-rays, so here, this is a, we know this is the detector. This is the detector and this is the, sorry, this is the X-ray tube. This is the detector and this is the sample holder. When these X-rays fall on the glass sample, if they have sufficient energy to dislodge the inner shell of the electrons of the sample, if they have sufficient energy to dislodge the inner shell electrons of the target material, you will get the characteristic X-ray spectra. In this characteristic X-ray spectra, we have two components. One is K alpha component, the other one is the K beta component. Actually, the K alpha component is again consisting of two parts. The first one is K alpha 1, second one is the K alpha 2 component. The wavelengths of K alpha 1 and K alpha 2 components are very close to each other. Because of that reason, we consider them as a monochromatic light radiation while doing the X-ray diffraction pattern. And in this case, we take the average of K alpha 1 and K alpha 2. So coming to next one. So this is the, so just now I told you this is the X-ray tube, this is the detector, this is the sample holder. When these X-rays fall on the sample, if they satisfy the Bragg's equation, that is 2d sin theta n lambda, if they satisfy the Bragg's equation, the constructive interference occurs and the peak or signal in intensity occurs. That is, if the X-rays, when the X-rays fall on the sample, surface of sample, if they satisfy the Bragg's law, we will get the peak or signal. So here those peaks or signals are received by the detector. Those signals are peaks are received by the detector. This detector is used to record and process the signals and also convert the signal into count rate. This count rate will be considered as the output. The output will be displayed in our computer. So finally, this is the way we will get the data in the X-ray diffraction patterns. After obtaining the data in the X-ray diffraction pattern, we need to draw a graph. So like this, by taking the 2 theta on X, and just now I told you why we are taking the 2 theta. So here this is 2 theta and this is the intensity. So this is the X-ray diffraction pattern of amorphous materials. Why this is the X-ray diffraction pattern of amorphous materials? Because in this no sharp peaks like this. Here this is the sharp peak. This is another sharp peak. This is the next sharp peak. So in this X-ray diffraction pattern, no sharp peaks have been observed, which is a characteristic of amorphous nature of the given glass samples are amorphous materials. So here and in between 20 and 30 degrees, so we have a broad hump. This broad hump represents that the short range periodicity of the prepared glass sample. Short range. fluidity of the prepared glass sample, and whereas these are the extra diffraction patterns of crystalline solids. Crystalline solids. In the crystalline solids, we may get the peaks like this. In the amorphous solids, we cannot get the peaks. So this is the difference between the extra diffraction pattern of amorphous and the crystalline solids. So based on these, so yeah, after obtaining these peaks, we need to go for the measurement of Miller indices. After measuring the Miller indices, we need to know or we come to know the structure of the given crystalline material. So this is about the X-ray diffraction patterns of the amorphous materials as well as the crystalline solids. Coming to the next one, second one is the UV visible. UV visible optical absorption spectra. UV visible optical absorption spectra is an important tool to understand the structure of the amorphous materials with various components. This is the actually this optical absorption spectra is used to find out the various optical parameters like absorption edge, cutoff wavelength, optical band gap energy, Urback energy, and so on. This is the Symagic spectrophotometer model UV3100 in the wavelength range of 200 to 1100 nanometers with spectral bandwidth of 3 nanometers. This experiment is there. It also is there in the Department of Physics, Usman University. Next one, this optical absorption occurs by various mechanisms, in all of which the photon energy will be Lambert's law. So before going to discuss about the Beer-Lambert's law, I'm going to explain the Beer's law. So here, this is the Beer's law. So according to this, the amount of light absorbed is proportional to the concentration of the absorbent substance. So here, it means that as the concentration of substance increases, the absorption of light also increases. So here, if the concentration decreases, the absorbance is also decreases. So this is the high concentrated sample. This is high concentrated sample in which the absorbance is more. Whereas this is the lighter concentrated sample in which the absorbance is less. This is known as the Gibbs. Next one is Lambert's law. Next one is Lambert's law. According to Lambert, amount of light absorbed is proportional to thickness of the absorbing material. It means that as thickness increases, the density of molecules or density of atoms also increases, hence more amount of light will be lost. So here, this is the high thickness sample and this is the lighter thickness sample. So here, if the thickness is more, absorption is more, whereas the thickness is less, absorption is also less. So finally, they have received this kind of results, hence they merged together to form a Beer-Lambert's law. So according to Beer-Lambert's law, the amount of light absorbed by the sample depends on the concentration and the thickness of a sample. This law is expressed through this equation, that is absorbance equal to log I naught by I. So this is the concept of the Beer-Lambert's law. And coming to the next one, so this is the UV visible spectrophotometer, and here this is the simplified schematic of main components in a UV visible spectrometer. Here I am not going to explain the internal part of the UV visible spectrometer. So coming to the after obtaining the results, we need to draw the graphs to determine the various optical parameters like optical band gap energy, Urback energy, and so on. So here, this is the optical absorption spectra. This is the optical absorption spectra of the prepared glass samples. From this optical absorption spectra, I need to give 3 important points. The first one is, so here at this position, no sharp edge has been found. At this position, no sharp edge has been found, which is a characteristic of glass nature or amorphous nature of the prepared glass samples. This is the first one. And second one is, so in this absorption spectra and enhanced absorption band. This is enhanced absorption band. In this absorption spectra, an enhanced absorption band was found at 470 nanometers, which is due to the 6A1G 41G transition of Mn2 plus ions in the octahedral symmetry. So here the position of this band, actually the position of this band was found to be restricted. Restricted means, so here the position of this band was displaced towards the higher valence sides from 0 to 0.8 mole percentage of MnO, from 0 to 0.8 mole percent of MnO, and later the band was blue shifted, that is shifted to lower valence side. So the shifting of these bands, to higher valence sides from 0 to 0.8 mole percentage of MnO represents that increment in the octahedral Mn2 plus ions at the expense of octahedral Mn3 plus ions. And next one, the intensity. So coming to intensity point, third point is intensity point. The intensity of the absorption factor also increases. This is a zero sample. In this sample, there is no MNO concentration. There is no MNO concentration, else we cannot get this peak. Don't expect the peak in this sample. And this is 0.2. Next one is green is 0.4. Next blue is 0.6. Next one is this is 0.8. And final one, this is the pink color 1 mole percent of MNO sample. So here the intensity of these peaks has been increased with increasing the concentration of MNO up to 0.8 mole percent of MNO. Later, the intensity is found to decrease. So, but what is the reason? So, the increment in the intensity up to 0.8 mole percent of MNO shows that the more number of octahedral Mn2 plus ions are exist up to 0.8 mole percentage. Later, the Mn2 plus ions are decreased, and this may also be due to the decrement in the average distance of Mn2 plus ions. Decrement in the average distance of Mn2 plus ions in the prepared glass sample up to 0.8 mole percent of MnO. Right. Actually, there are three methods. There are three different methods to obtain the various optical parameters of the glasses, such as optical band gap and Urbax energy. There are first one is Gauss method, second one is the ASF method, third one is the DASF method. So coming to the first one, first method, Gauss method. So Gauss method, in this Gauss method, the measurement of in this Gauss method to determine the optical band gap energy, the measurement of absorption coefficient as a function of energy of the incident photon is required or should be required, which is based on the thickness of the glass sample. It means that to obtain the indirect band gap in this Gauss method, the thickness of the glass sample is compulsory. Without the thickness of the glass sample, we cannot determine the band gap of the given sample. Whereas here coming second method, ASF method, in the ASF method, to determine the optical band gap energy, no thickness is required or thickness is not required because it is purely based on the absorbance of the glass sample. And coming to third method, DASF method, this is a simple derivative of the ASF method. The DASF method is the derivative of the absorption spectrum fitting method, and in this method also the thickness of the glass sample is not required. And this method is used to measure the type of optical transitions more precisely than the Gauss method and ASF method. That's why the DASF method is more accurate than the Gauss method and ASF method. And here I'm very proud to inform you that I am the first person published a paper on these three methods in the last month. So coming to the next one, Gauss method. Gauss method. The Gauss method. In this, we are going to evaluate the optical parameters like optical band gap energy and Urbax energy. So the optical absorption coefficient near the fundamental absorption edge of each curve is evaluated by the formula alpha nu equal 1 by d to ln I naught by I. Here just now I told you this is the Beer-Lambert's law. This is the Beer ln log I naught by I. Log I naught by I is the Beer-Lambert's law. 1 by d is nothing but your thickness of the sample. So that's why I told you just now. So the optical absorption spectra is purely based on the Beer-Lambert's law. And next one, the amorphous materials in fundamental absorption region obey the following relation alpha nu equal to B into H nu minus E of whole power n by H nu. Here n is index. But for most of the amorphous materials, n equal to transitions are suitable or favorable. So here these are the right. These are the tau plots of prepared glass materials or glass samples. These tau plots are used to determine the indirect band gap values, and these are Urbax plots. These Urbax plots are used to determine the Urbax energy values. Urbax energy is nothing but degree of disorderness. This degree of disorder, I think you have said about the degree of disorder in your intermediate chemistry. So here, coming to tau plots, so here these tau plots are drawn by taking the HU values on x-axis and alpha is whole power 1 by 2 on y-axis. So here, this is the x-intercept. The x-intercept of linear portion of the curve. This is the linear portion of the curve. The x-intercept of linear portion of the curve gives the indirect band gap energy of the given prepared given sample. So here, from this curve, I can say that the indirect band gap values are decreased with increase in the concentration of MnO up to 0.8 mole percentage, and later the indirect band gap values are increased. So here, the decrement in the indirect band gap values. The decrement in the indirect band gap values up to 0.8 mole percent of MnO shows that there is an increment in the non-bridging oxidants due to the incorporation of MnO ions in the prepared glass sample. It means that the non-bridging oxidants are increased from 0 to 0.8 mole percent of MnO. Later, the non-bridging oxidants are decreased, that is at 1 mole percent of MnO. And coming to the next one, these are Urbach energy values, and these are Urbach graphs or Urbach plots. With the help of these plots, we can determine Urbach energy values. Urbach energy is nothing but degree of disorder. So here, by taking the reciprocals of the slopes of linear portion. So here, reciprocal of this is the actual, this is the linear portion. This is the linear portion. On the linear portion, we need to calculate the slope. After obtaining slope, we need to go for the inverse slope. So the reciprocal of the slope, the reciprocal of the slopes of linear portion of the curve gives the Urbach energy values. From this graph, I can conclude that the Urbach energy values are increased with increasing the concentration of MnO up to 0.1%. Later, the Urbach energy values are found to decrease. The increment in the Urbach energy up to 0.8 more percentage shows that there are so many number of defects in the prepared glass samples. Due to defects, tumbling bands are developed in these prepared glass samples. Right. So here coming to second method, the second method is ASF method, that is absorption spectrum fitting method. So this is the graph optical absorption spectrum of the prepared glass sample. In ASF method, here I have drawn by taking energy on x-axis and absorbance on y-axis. And next one, so here this is the plot of 1 by lambda and a by lambda whole power 1 by 2. With the help of these plots, we can calculate the indirect bandgap values of the prepared glass samples. From these plots also, I can conclude that the indirect bandgap values are decreased up to 0.8 mole percent. Later, the indirect bandgap values are found to increase. So the decrement in the indirect bandgap values up to 0.8 mole percent MnO shows that the increment in the MBOs. If there is a decrement in the energy gap, there is an increment. There is an increment in the formation of MBOs at the expense of bridging oxidants. Coming to the next one, this is the plot which can be used to determine this is the Urbach plot actually. So these are the plots which I have drawn between the 1 by lambda and ln absorption, log of absorption. So with the help of these graphs, we can determine the Urbach energy values. From these plots, I can conclude that the Urbach energy values are increased up to 0.8 mole percent. Later, the Urbach energy values found to decrease. Coming to DSR method, so here just I told you, and the first person did this method in India. So here this is the plot of so here this is the DSR method plots, which is drawn between 1 by lambda and the derivative of ln a by lambda. So here this is the peak. Actually, this is the first sample, second sample, third sample, fourth one, fifth one, sixth one. So this is the highest peak. So here by taking the highest peak value and multiplying with the multiplication of the inverse of highest peak value, the multiplication of inverse of highest peak value with the HC value, HC is about 1240. With HC value, we will get the indirect bandgap value. Indirect bandgap value. So from these plots, I have measured all the indirect bandgap values and I have calculated in the given tabular form. From this spectra, the same trend was observed. That is, whatever the trend was observed in the Gauss method and ASF method, the same trend was observed in this method in case of indirect bandgap values. That is, the indirect bandgap values are decreased up to 0.81%. Later, the indirect bandgap values are to increase. And next one, this is the plot of ln 1 by lambda minus 1 by lambda g, ln absorption by lambda. These plots are used to measure the Urbach energy values. From these plots, we can conclude that the Urbach energy values are increased up to 0.8 mole percent of MnO. So here, this is the comparison of optical bandgap values of the prepared glass sample in using ASF and DSF methods. Actually, in these three methods, Gauss method, ASF method, and DSF method, the same kind of trend was observed. In the three methods, the same kind of trend was observed while determining the indirect bandgap energy values and optical Urbach energy values. From this, I can conclude that there is an excellent agreement between the Gauss among these three methods. So coming to EPR spectra, so your electron parameter resonance spectra is one of the most efficient technique for the calculation of local symmetry. And this spectroscopy detects the unpaired electrons available in the prepared glass samples. So this is the dual 1x EPR spectrometer that works in expanded frequency range with 100 kHz field modulation. This instrument is there in the Department of Chemistry, University of Hyderabad, that is Central University. So coming to the resonance condition. So the resonance condition for the absorption of radiation in EPR spectroscopy is delta equal to h nu G beta B. Here G B is the Landis diffraction, beta B is the Bohr magneton, and B is the upward magnetic field. So here this is the EPR spectrum of the prepared glass sample. Actually, in the base sample or in the M0 sample, there is no M1 ions. There are no M1 ions. If there are no M1 ions, we cannot get the EPR spectrum for that sample. That's why here I have got the keys only for 5 samples. That is, this is 0.2 sample, 0.4 sample, 0.6 sample, 0.8 sample, and 1 mole percentage of MNO sample. So here, this is here after drawing these graphs, here I have observed one peak. Here I have observed the resonance peak or resonance signal at G equal to 2.0, and the second one is at G equals 3.1, and third one is at G equal to 4.3. So the peak or signal at G equal to 2.0 confirms the HFS, that is predominant 6-9 hyperfine structure. Actually, if this G value, is less than the pre-electron G value, the pre-electron G value is 2.0023. This G value is less than the pre-electron G value. If this value is less than the pre-electron G value, we can say that the prepared glass samples are amorphous solids, or the prepared glass samples are having the non-crystalline nature. So yeah, next coming to the next parameter is another beautiful parameter. So yeah, I hope I think only few researchers have done this method. So yeah, this is hyperfine splitting constant. Hyperfine splitting constant. This hyperfine splitting constant is used to find out the nature of the sample. That is either ionic nature or covalent nature of the given given or prepared sample. So this is the formula. This is a formula which can be used to find out the hyperfine constant value. To find out the hyperfine constant value, I am going to use to find out the hyperfine constant value. Here I have used the EPR spectrum of one sample. EPR spectrum of one sample. So here this is the first peak. This is the first peak. Next one is the first crust. This is the crest, first crest, second crest, third crest, fourth one, fifth one, and the sixth one. Six crests are there, and this is the first crust. Like that, six crusts are there. This is the first one, second one, third one, fourth one, fifth one, sixth one. So how many number of crests are there in this graph? That many number of crusts are there. So here, based on this formula. But how can we get these values? Delta OPP. What is meant by delta OPP? Delta OPP represents that the distance between the first peak and sixth peak. The delta OPP reference gives that the distance between the first peak and the sixth peak, and delta OTT gives that represents that the distance between the first trough and the sixth trough. Next one, delta MPP. Delta MPP represents that the distance between the second peak and the fifth peak. Delta MTT represents that the distance between the second trough and the fifth trough. Similarly, so here delta IPP is nothing but the distance between the third peak and the fourth peak, whereas delta ITT represents that the distance between the third trough and the fourth trough. So after finding these values, substituting those values in this formula to obtain the hyperfine constant. So here if the hyperfine constant value is above 60, if the hyperfine constant value is above 60, we can say that the prepared glass samples are ionic in nature. So here the insert diagram. This is the insert diagram. In the insert, I have mentioned the hyperfine constant of hyperfine constant values of 5 samples, 0.2 sample, 0.4 sample, 0.6 sample, 0.8, and 1 mole percent of sample. From this graph, I can conclude that the hyperfine constant values are increased up to 0.8 mole percent of MNO, and later the hyperfine constant value is found to decrease. And here in this graph, at for 0.8 mole percent of MNO, the hyperfine constant value is around 92 into 10 to the power minus 4 centimeter inverse. If this value is above the actually this value is above 60, that's why the prepared glass samples are ionic in nature. So next one, so here based on EPR spectroscopy, here I have measured the number of students participating in the resonance. That's how I told you the basic principle behind EPR is the resonance phenomena. So here these are the formulas which can be used to measure the number of students participating in the resonance and parametric testability. Based on these principles, I have measured the number of students participating in the resonance as well as parametric testability. So here from those principles, the values are calculated, and here they based on them, here I have plotted the graphs. So here, from this graph, I can conclude that, or I can say that the number of spins participating in the resonance are increased up to 0.8 mole percent of MNO. Later, the number of spins are decreased. It also shows that up to 0.8 mole percent of MNO, the Mn2 after lateral Mn2 plus ions are increased at the expense of after lateral Mn3 plus ions. So this is a graph which shows the param and susceptibility. Here also up to 0.81% the susceptibility is increasing, and later it is decreasing. And next one, this is another beautiful concept, that is zero field splitting parameters. So a zero field splitting parameters refers to the splitting of spin levels in the absence of magnetic field, and it mainly occurs in the transition metal complexes where there are more number of unpaired electrons. If there are more number of unpaired electrons, definitely we will go for the determination of zero field splitting parameters. This is the formula which can be used to determine the zero field splitting parameters. So finally, based on the values, I have drawn the graph. So here also the zero field splitting parameters are increased up to 0.8 mole percent of MnMo. Later the zero field splitting parameter value is found to be decreased. It means that up to 0.8 mole percent of MnMo, the after Mn2 plus it also shows that up to 0.8 mole percent of MnMo, the after Mn2 plus ions are increased at the expense of after Mn3 plus ions in the prepared glass samples. So with this, I'm going to wind up my session. So coming to conclusions, the XRD pattern confirms the amorphous rate of the given prepared samples. Next one, optical spectra is used to determine the indirect band gap and Urba's energy values. So based on indirect band gap and Urba's energy values, I can conclude that the indirect band gap values are decreased with increasing the concentration of MnMo up to 0.8 mole percentage, which shows that the more number of non-bridging oxygens are developed or created at the expense of the bridging oxygens. And finally, so here the hyperfine splitting constant shows that the prepared glass samples are ionic in nature. Why the prepared glass samples are ionic in nature? Because the hyperfine constant is very high, which is equal to 92 into 10 to the power minus 4 centimeters. That's why the prepared glass samples are ionic in nature. Thank you.
The next session is continued with Dr. C. Pirwal, sir. So little short introduction about Pirwal. Dr. C. Pirwal has completed his PhD in 2016 from IIT Madras. He worked as a postdoctoral research fellow at IIT Delhi from 2016 to 17. Currently, he is working as an assistant professor in the Department of Humanities and Sciences, that's physics, and his research interests includes ferroelectrics, piezoelectrics, magnetoelectric nanocomposites, ionic polymer metal composites, based sensors, and actuators for soft robotic applications. He published 23 research articles in peer-reviewed, well-reputed international journals, and he was granted with a patent from his PhD work. He also presented his work at various international conferences. He is currently executing two R&D projects funded by DRDO and DST of worth 25 lakhs. He is also a member IEEE and faculty advisor for Nanotechnology Council at VNRVJIET. In simple, he is a front and back of this 4-day event. Now I request Dr. C. Pirwal to continue the session. Thank you. Sir, please continue the session.
Yes. Hello. Thank you, sir. Very good afternoon, one and all. So sir already explained about the important technique that we have to do when you are trying to understand the material, especially the material structure. Am I audible to you? Yes, students. Last, can you hear me? Yes. So here, before going to start the X-ray diffraction, let us try to understand why we need to understand the structure of the material. For example, there are atoms are sitting here in the rows, right? Then I am the electron now. I can easily run wherever there is space. I can run easily between these two rows. But if the atoms are actually randomly distributed, can this electron can easily move? That's not possible, right? So that means the behavior of electron can be understood by understanding the atomic arrangement in a given material, right? So this atomic arrangement can be studied using something called X-ray diffraction. Okay. Today I'm going to explain the very basic phenomenon or basic principles of X-ray diffraction.
to introduce you especially to the BTech students, please. Next. You can see the X-rays were discovered in 1895 by Röntgen, for which he got the Nobel Prize, followed by the first diffraction experiment by X-rays done in 1914 by von Leeuwenhoek. He also got Nobel Prize. Next, followed by 1915. So the theory was given by Braggs to determine the crystal structure. You can see again he got the Nobel Prize. Later, in 1953, the DNA structure was solved by Watson and Crick. They also got Nobel Prize. So this many Nobel Prizes are given to this particular concept of X-ray diffraction. Then you can understand the importance of particular X-ray diffraction, right? Yeah. So as I explained previously, if you take a crystalline material, the atoms are arranged regularly, right, in a periodic fashion. Whereas if you take polycrystalline material, in polycrystalline material, entire material is not going to have single arrangement of atoms. Instead, there will be some breaks. Like in a particular region, you can see here, this region they are oriented in particular direction, and this region they are oriented in other direction. But within a small region, they are arranged properly. So polycrystalline way, it is a mixture of this kind of crystalline materials. It is a combination of so many crystalline materials. Whereas in amorphous, there is no correlation. You can see they are randomly distributed. Atoms are arranged randomly distributed. Now, to see the atomic arrangement in general in any material, there are 14 ways we can actually we can arrange the atoms in a given material. Whatever the material that you're touching today, hundreds of materials you're touching, starting from your mobile phone, computer, whatever you touch. Okay, now in that material, the atoms are arranged either of these 14 ways only, no other way, or amorphous. To take a crystalline material, so these are the 14 ways one can actually arrange the atoms. First one is cubic. In cubic, you may be having primitive. Primitive means the atoms will be placing only at the corners. Whereas in body center, there will be an extra atom at the body center. To take face center, apart from the corner, you can also have the atoms at the face centers. Like that, we have classified these crystal systems into 7. Starting from cubic, tetragonal, orthorhombic, monoclinic, triclinic, tetragonal, and finally hexagonal. These are the various types of crystal systems, and we can have these 14 ways of arrangement in the given material. Yeah, this arrangement, you can see the how they are arranged. For example, if you take the distance between, let's say, two atoms along x-axis, that is A, along y-axis, that is B, and along z-axis, that is C. It means that called lattice parameters. And how much will be the angle between these axes? Okay, that means these angles and the distance between two successive atoms because the lattice parameters. And based on these values, these are only possible ways. There is no other way that is available in the nature. So if you take any material, in that the atoms are arranged in either of these 10 crystal systems or the 14 way of arrangements. That's what I showed previously. Now, if you see the three-dimensional crystal, how it will be looking like. Whatever the crystal that you are touching today, that will be in the particular 7 crystal systems. In the 7 crystal system, if I have taken, for example, a physical system and explained it in three dimension, how the atoms are arranged, and this is the crystal. You can take the atoms are arranged regularly, periodically in the three dimension, right? Now, if the question comes, right, $1 question for which we have given actually, no, how many Nobel Prizes? I think 4 or 5 Nobel Prizes. I have shown the first one, right? So, why the question is this one? How do we identify the arrangement of atoms? Okay, what do you mean by arrangement of atoms? There is nothing but the structure. How do we know the structure of the material? That means you are going to understand the atomic arrangement in a given material. Yeah, you can see this can be done using diffraction experiment. So you know diffraction means you are already studied in your plus 2 level, right? What is the diffraction? Just bending of light into sharp edges followed by the superposition between the secondary wavefronts to give you an alternative dark and bright finish on the screen. Look at this diagram. This is the slit. Okay, na? Or aperture you can take. The light wave is incident here. This is getting spreaded, and when spreading, bending is also happening here. So while traveling, they are actually getting superposed each other. That already explained the constructive and destructive interferences. Those things are happening in this region, because of which you are going to get a redistributed intensity pattern rather than uniform intensity pattern. So this particular thing can also happen in your material, because you can see we need a slit to have the diffraction. You can see between the two atoms there is a gap that is going to act like your slit. That means if you take a crystal, we have regular arrangement of atoms, so and we also have some gaps. So these atoms are going to act like obstacles, through which if you are sending this particular light, then what happens? They can diffract, and if I analyze the diffraction pattern, then one can understand the atomic arrangement. Here you get the diffraction always, but it will be greater. It will be enhanced only when there is a particular condition. If the size of the gap or the size of the obstacle is similar to wavelength of the wave that you are using. That means, for example, if I am taking this particular atomic arrangement, the distance between two successive atoms will be in the order of angstroms. The order of angstrom. So I have to use a wavelength which is in the order of angstroms. So if you take the electromagnetic spectrum, you can see in electromagnetic spectrum which will be having order of angstroms. You can see X-rays are there. So that's the reason why people started using X-rays to do the diffraction experiment, so that they can get the diffraction pattern and analyze that, will get the arrangement of atoms. Yeah, this is simple X-ray diffraction. There is a source of X-ray. Sir already explained how the X-rays are produced, and there is a slit, and this is just to focus the X-ray beam onto your crystal. Once this crystal is incident with the X-rays, you can see because of the atomic arrangement, you are going to get the diffraction pattern on the screen. So this is a typical diffraction geometry, and this is the diffractometer. So this diffractometer should be the cost of maybe Indian rupees, we take maybe 2 crores and 3 crores. We have used in our PhDs, so the diffraction experiment of approximately 3.5 crore. So these are the very efficient and sophisticated instruments where we are getting information about the arrangement of atoms. That's the reason why we are spending a lot of money. And you can see here, this is a polycrystalline sample where you can see the tiny crystals. Once the X-rays incident on these tiny crystals, the combination of tiny crystals, you can expect scattering and diffraction. This diffraction pattern, if you see, are already explained. The diffraction peak will be coming for the crystalline samples only. Here, we have taken polycrystalline sample, and what is special about this diffraction pattern? It's nothing but the intensity distribution after the experiment that we get. And you can say pattern is unique to the material. No two materials will be having two similar patterns. For example, you have 1 lakh materials. 1 lakh materials will be having different patterns. Nothing will be matching. For example, if you take the peak position, okay, now the width of the peak, everything will be different for different materials. That's how they're able to detect what type of material it is. For example, you got some material, you don't know what it is. Just bring it and perform the diffraction experiment and analyze it using the computer software which is already programmed, which knows. Okay, now then we understand what is the material exactly. Starting from the atomic, the composition, how many atoms are there in that, you can exactly come to know from this particular experiment. That's the reason why the pattern is unique to the material. It is like our fingerprint. Okay, na? The material fingerprint is X-ray diffraction pattern. Yeah, that's the basic law behind this is diffraction, and it is governed by this Bragg's equation, diffraction condition, constructive interference, and this is how the polycrystalline material will show the different peaks, whereas amorphous material will show only a broad hump. It may not be peak. So by looking at these diagrams itself, we can say first thing is whether the given material is a crystalline material or amorphous material. If it is crystalline material, then we have to actually analyze the experimental data to understand what is the separation between two successive atoms and at what angle they are oriented. What is the structure? You can actually try to understand from this particular experiment. Yeah, and one more thing is in nanomaterials, we can also calculate using this extra diffractometer is the crystallite size. That means, crystal means in which the atoms are arranged regularly. If you take polycrystal material, it is not uniform everywhere, right? There are small crystals are available. So what is the one small crystal size, average crystal size we can get using this Scherer formula? Okay, na? So this basically we can calculate from the diffraction pattern, and by taking the width of the diffraction pattern, we can calculate the crystal size using this particular Scherer formula. Yeah, the applications are not limited for this X-ray diffraction. One can determine the crystal structure. It's going to be the fingerprint for the material. Then you can also identify the phase. Okay, what is the atoms? What are the elements are present, and how they are arranged? You can understand the grain size. You can also see the micro strain. Sometimes what happens is while the arrangement of atoms during the formation of material, there may be some strains. How much is the strain inside that material, that also can be understood. And texture again, we can calculate texture and stress, or if there are any stresses in the material, we can also determine them. And determination of composition of the materials, especially thin films, you can measure use, you can use this particular technique. And identification of archaeological materials, right? You got some material, but you don't know what it is, what type of material it is. How are you coming to know that? Because if you do the experiment, you can understand exactly what is the material that is. Okay, no? These are the applications, not limited, but there are large many applications of X-ray diffraction. I have kept only that few. Yeah, with this, I would like to conclude my session. So this basic idea of this particular session is the X-ray diffraction is a fundamental technique. Whatever the material that you're touching, every material has been undergone this particular measurement. If you invent some material, the first experiment that we have to do is X-ray diffraction. So every student and every scientist and every researcher who is dealing with materials, directly or indirectly, should know the basic experiment. That is the purpose of this particular session. That's why we have given a little bit elaboration and understanding how these X-rays are exactly giving information about the atomic arrangement. So with this, I am concluding, sir.
Thank you, sir. It's time for the questions. So I request students to have any questions. Dr. V. Ashok sir is also available here. If you have any queries or any questions on this, so please come forward for the questions. But personally, sir, Ashok sir, I have one question. So zero field splitting parameters you said. Can you tell me what's the use of calculating that zero splitting parameters?
Actually, okay, in the zero field splitting parameters, to determine its value, we need to measure the peak intensities. So based on the peak intensities, we can find out the zero field. And this zero field intensity is used to zero to find out how many number of Mn2 plus ions are there up to a 0.8 mole percentage, and that how they are decreasing.
Thank you, sir. Students, any questions from your side? Please come forward.
Good afternoon, sir. I'm Sir. Sir, basically, if we calculate, you mentioned about K alpha lines while giving the exam. So, what is the wavelength of the source at which we use this basically?
The wavelength of source is 1.5418 angstroms. Actually, this is the average wavelength of K alpha 1 and K alpha 2. 1.5418 angstroms.
Okay, like if we convert it into nanometers, then if we convert it into nanometers, it will be 0.154. So then, if we calculate its energy of X-rays, probably I forgot the figure, but it will be around 9,000 electron volts. But when we talk about photoelectric effect in quantum mechanics, every metal or every compound will have certain work function attached to it. So it will be something. It won't be. It won't exceed 100. Basically, even if it is so hard crystal, its work function. Yeah, 100. So energy. So I'm talking about work function. So it will be in terms of energy, electron volts. So let's say we have a compound which has a 10 electron volts, and we are able to study its X-ray diffraction. So like we are using X-ray source with an energy of around 9,000 electron volts, and we are striking these so energetic X-rays on a surface which has a reasonably very low work function. So my doubt is, like when we strike these XRDs on the surface, the electrons the electrons in whether it may be crystal or amorphous, whatever it may be, the basic XRD phenomena, X-rays will come and interact with the electron and it diffracts. Yeah. So whenever these X-rays, so energetic X-rays, interact with the electrons, electrons have to be removed, right? Yeah.
Actually, yes, you're right. But there are not only this diffraction is happening there. Apart from diffraction, there are other phenomena like emission of electrons will be happening. So that depends upon the source of the detector which you are using. I'm using a detector to detect my diffracted X-rays. There are, of course, emission of electrons will be there, but you are not having the detector in that particular instrument. There's another experiment where you can detect the electrons and study something else. I hope you got the point.
Then if the electrons if the electron got ejected, then automatically the structure of the compound will change. So it won't be the structure of the compound which we prepared. The structure of the compound will vary because the electron is not off from the surface. Yeah, the structure is being preserved. But what is the reason behind the structure being preserved even after hitting the surface with the so energetic X-rays by following a photoelectric effect?
If you remove one or two electrons from the surface, structure will not be affected because we are discussing about the atoms. Atoms are not going anywhere. I'm just spending 100 rupees from my pocket where I have 1,000 rupees in my pocket. So I'm not going anywhere. You got my point, right? So atom is spending only few electrons, but doesn't matter. Doesn't matter. It's not changing its position. If it is changing its position, then the problem. Atom is stable there, right? Atom is not changing its position. Structure will change if you change the position. If you take a cube, cubical shape become tetragonal if you extend this atom to some more height. No. You have to understand the X-rays are not penetrating into the material. It will be approximately 10 micrometers. You can expect. In the 10 micrometers only, it's unlikely. I have taken, let's say, 1 mm thickness of sample. It will not go into the 1 mm thickness of sample. That's the point.
What you are saying is that is like the energy you are giving is the to remove the electron. The first point that is clear. Next point is why atoms are not coming is what is the energy of atoms in the solid. If you give that much energy, the ions will come out from the solid. Whether you are given that much energy is a question. Binding energy.
We are not breaking the bonds. That's clear, right? We are not breaking the bonds between the ions and atoms. Yeah. Okay, now some of the doubts you can discuss.
what it means, the voltage is required to those electrons. The minimum energy required for the to knock off the topics or it or what it can
That's what I'm saying. The knockout electron doesn't matter for me. I'm not changing my position. See, X-rays will see the obstacle. Obstacle is not changing its position. I hope it is clear.
The bonding is changing, what are the supplementary changes?
constant. Yeah, other is the constant, but electron deficiency is happening. How many times?
Yes, excellent question from the students. This kind of questions definitely encourage the speakers to talk more. But as a time frame, I'm sorry for the disturbance. So, sir are always available in the college itself. Whenever you're free and sir is free, happily you can discuss. So I'm sorry for disturbing because I need to continue with the remaining sessions. In conclusion, and any other doubts, please come forward.
He's a scholar. He's a scholar. So that's why he's getting.
Yeah, research scholar. So very nice. So you can have a discussion afterwards with faculty. Yes.
Understand, right? Students, if you enter into research, things will be in different manner. Understand? So, we are spending years together on research to understand small things.
Yes. In summary, so for this talk, in summary, Dr. B. Ashok sir started with the classification of solids and introduced the borate glasses and its importance in the glass preparation. And that's a doping with the transition metal ions and how the physical, optical, and structural properties vary in case of doping with the MNO. And he also focused on working of X-ray diffraction, UV visible spectroscopy, and optical absorption spectra. And the organizing team congratulating Dr. Ashok sir for publishing the first paper on three methods in India. And however, like a small introduction to zero field splitting parameters also encourages to do the work towards that. And in continuation to that, Dr. Thirumal sir has started with Nobel Prize. So what I understand from the talk is to get Nobel Prize, definitely to do work on X-rays, because almost 3 to 4 members got that. In continuation, the importance of X-ray diffraction in crystal studies and the calculation of crystallite size that was also explained by sir. So all these things are definitely encourage the students and learners to work towards the material characteristics. So once again, I thank Dr. Ashok sir and Dr. Thirumal sir to give a valuable lecture on these characteristics. So in continuation, the next session is on thermal characterization of nanomaterials, the DSC, TGA, DTS studies. And this session was given by Dr. L. Srinivas Rao sir. And Dr. L. Srinivas Rao sir has been working as an assistant professor in VNRVJIET, Hyderabad for last 7 years. He has 20 years of teaching experience and research experience. Dr. Rao has contributed his research work in the area of oxide glasses, dielectrics, laser force, ZNO nanocomposites, transparent ceramics, starch-based biodegradable plastics. He has completed his post-graduation in engineering physics in distinction in 2002 from Kakatiya University. He has completed MPhil in condensed matter physics in 2005 in A grade and subsequently PhD on condensed matter physics in 2008 from Acharya Nagarjuna University. He has done PG Diploma in Telecommunication from University of Hyderabad in 2011. Dr. Rao has published 39 research articles in various Scopus, WS, and SCI indexed journals. He published a book chapter on medical applications of bioglass ceramics. He published a patent on development of luminescent ceramics. Also, he has attended 40 national conferences or seminars and 6 international conferences. He is a reviewer and member of editorial board for various elsewhere journals such as Journal of Alloys and Compounds, Compounds and Materials Chemistry and Physics, Journal of Non-Crystalline Solids, and so on. He is the life member in Optical Society of India and Materials Research Society in India. Dr. Rao has received Best Teacher Award in 2019, presented by Impact Foundation India, and he received the Faculty Excellence Award 2025 by at Emigo Global Education, Hyderabad. Now, Dr. Rao has completed a research project on magnetic ceramics funded by TechWip 3 JTUH worth of 2.5 lakhs as a principal investigator. Now he's working on a project, ceramic phosphorus funded by UGCDAE CSR worth 7.75 lakhs as a principal investigator, and also is working on another project on 3D imaging by lasers funded by DRDO worth 52.26 lakhs as co-principal investigator. With this introduction, I request Dr. L. Srinivasarao sir to continue the session. Sir, please start the session.
Thank you very much, sir, for your nice introduction. Good afternoon, all of you. Yes, good afternoon, all of you, students. Am I audible to you? Last students? Yeah. My talk today is on thermal characterization of nanomaterials with three techniques. This is nothing but the heat-related experiments on DSE, DTA, and TGA. Here, I take one example of characterization. We prepare the materials, which are nothing but the nanoglass ceramics. We characterize those nanoglass ceramics with the help of these thermal studies. Here, before going to actual topic, let us see the basic introduction. You are aware of micron size. What is micron size of a material or system? What is the order of micron? 10 power minus 6 meter. So when we consider any material, a bulk material, in that we can identify group of atoms, group of molecules, clusters or grains. If we determine their size, then we see their size is in the order of 10 power minus 6 meters. Now, by doing something else for that material, if we squeeze the size of the material 1000 times, we have to decrease the size of the interior grains into 1000 times, then that goes to 10 power minus 9 meter. So the materials in which the grains or the group of atoms or clusters, they are in the order of less than 100 nanometer in at least one dimension are known as the nanomaterials. So suppose if I use this plastic material, in this plastic material, the grains or the molecular structure, they exhibit in the micron size. By doing something, if I squeeze the interiors or crystallites or grains 1000 times, then this pen is becoming like a nano pen. Both are observable, and we can see the different physical appearance. But which is more dense or which is more rigid means nano pen. Why? Because all the clusters or grains are squeezed by 1000 times. So here the nano scale is the important, in which we reduce the size of the systems inside the materials. Here we have to understand two terms. One is the nanoscience, another one is the nanotechnology. This nanoscience is actually the part of physicists and scientists, whereas this nanotechnology is the part of engineering students, engineers or technologists. So here what we do, we study the phenomena, what is the basic phenomena involved in the nanoscience, nanomaterials. How do we get the squeezing of the size by 1000 times when we compare with the ordinary materials? We study the phenomena. And after that, after squeezing the size by 1000 times, we understand the properties. After understanding that, we give this is the behavior of the particle, this is the behavior of the nanomaterial. Then the part of the engineers is that they have to characterize such materials where they can be suitable for the potential applications. Thereby, they have to produce the goods and they have to design the goods for the consumers or customers in the daily life. That is the part of nanotechnology. Here, the size is the matter here, which is nothing but the structure of the material system, property of the material system. We see the gold cube here, gold biscuit here. It is of 99.99 purity. It appears in yellow color gold in ordinary state, in bulk state. Here the grain sizes are in the order of microns. Whereas when we convert this into nanoscale, then its band gap changes. As the band gap is changing, obviously its wavelength is changing. You know the relation between the band gap and wavelength. What is that? What is the band gap and wavelength relationship? Eg equals to, say, yeah, SC by lambda. So Eg is inversely proportional to the wavelength. As band gap is increasing, wavelength decreasing. So that there is the shift of the wavelength towards the blue region. That is known as the blue shift. Sometimes the reverse process may take place depending on the material composition. Then we get the red shift also by squeezing the band gap. Here we can understand the nanoscale concept. Here if we see the atom's size, it is in the order of 1 angstrom, molecules 1 nanometer, DNA 10 nanometer, viruses 100 nanometer. So here all these compositions, they come under the nanomaterials composition. And when we see bacteria, human hair, and basketball, then they are the ordinary materials with more micron size of the ingredients. So here we have to prepare these materials first, which are nothing but the ordinary materials. Later, by doing some techniques, we make them as the nanomaterials. That is the objective. Yeah. So we need not worry about the research on any other fields like the space technology, cosmos and all. There is the plenty at the bottom of the room. The lecture was given at the American Physical Society meeting on December 29, 1959. He is the father of nanotechnology. He is Richard Feynman. So if we conduct the research at the bottom of the room, then we get more things which can be applicable for the present day technology. Next slide. Here, nanoscience is nothing but the we imitate or we copy the things from nature so that we do something else in the laboratory. Okay, that is known as the nanoscience biomimicry. Biomimicry means we identify the biological aspects in our daily life and we copy the same things. We apply the same methodologies for our requirement for general materials. Next, sir. Yeah. This is the sticky feet of lizards, geckos. Then when we see their sticky feet, you can see small hair or small fibers here, so that they get a good connection when they are on the walls or they are on the trees. So here they give more attachment or more force to stick towards the walls or trees. Next, sir. Next. This is the spider silk. It is also giving the strength. It is also in the nanoscale. Actually, here it's a longitudinal strength and the bending strength is very good, much enough. And we use the same technique in our nano wires or nano tubes also. Next. Here, this is very, very important concept. This is the self-healing butterfly. Here, the layer on the wings of the butterfly is coated with some nano powder that is with the hydrophobic. The water cannot touch it. So we use the same concept in the automobile engineering so that we prepare the nano paints. Thereby, if we paint the nano paint on the car surface, then no water touch the car surface. There is no rust or there is no need to clean the car always. So it is the self-cleaning technology is from that one. Next. Optical nanoscience. Here, if we see the wings of small creatures like this, orthopedic creatures, then they exhibit some colors on their wings like this. Okay, beautiful colors. This is nothing but the luminescence. What we call it is the bioluminescence. We know the luminescence is nothing but accepting the energy in any form, releasing the same energy in the form of light, and they automatically adjust their metabolism such that they adjust their band gap actually in the molecular level. So when the band gap is adjusted, automatically wavelength is adjusted. Wavelength is adjusted, their color appearance is also adjusted. And the same principle is used by the gecko in the forests or on the trees. Gecko changes its colors as per the temperature, as per the environment. That's auto adjustment is nothing but the channelizing the energy band gap. That is known as the band gap engineering. That is the optical phenomenon. Next, sir. Water collecting orthopedic creatures. Next, sir. Next. Here we can get an infinite number of examples in our nature to learn something and to copy something else so that we can do our work in our laboratory. I have followed the same technique. I copied the same technique from the nature only, and we prepared the nano glass ceramics. That's what I am going to showcase you. And then technically, I am going to characterize the same materials with thermal features. Here, this nanotechnology is not new. It is the older technology in the ancient history of Africa or some Greek. You can see the availability of the nano paints in which they use the melting of gold and silver nanoparticles in colors so that they paint the walls or they paint the photographs or pictures. Still today, they are with the same intensity. They are not fading out. That is just because of the nano size colors. And here, the phenomena involved in this nanotechnology is based on the nanoscience. This nanoscience includes two concepts fundamentally. One is the increased surface to volume ratio. Second one is the quantum confinement. Let us identify what is increased surface to volume ratio here. Let us consider a sphere. This is the sphere with a 3 micron size. Now I am decreasing the size of the sphere to 2 micron size. And again I am decreasing the sphere size to 1 micron size. Say for example, here we have 3 spheres of sizes 1 micron, 2 micron and 3 micron. Now let us determine the surface to volume ratio of these 3 spheres. Then here the surface area is given by 4 pi r square. Volume is 4/3 pi r cube. So here this S by B surface to volume ratio is 3 by r. This means that when this r is decreasing means radius of the material is decreasing, ball is decreasing, then this surface to volume ratio is increasing. That means the outer part that is interacting with the other materials surroundings is increasing. In the same material, in its bulk state, its surface to volume ratio is less. Whereas in the nano state, it is more. For example, suppose if we take a 1 cube sugar crystal of 1 kg, 1 kg sugar crystal is there. Imagine it. From the sugar factory, we are generating it as the granules of small micro sugar crystals, like 1 milligram. So if you want to make a tea for 100 members, one person is using the bulk 1 kg sugar crystal to make ready the tea, and another person is using the granules of 1 milligram size only. Who can melt the sugar fast? First person or second person? Second person. Why? I have provided only 1 kg both of them now. Why? Because the outer area, the surface area of the same content is more in second case. In other words, surface to volume ratio is enhanced. So that the surface area, the atoms on the surface of such sugar can interact with other ingredients in the tea, and you can make that tea easily. That means the chemical reaction rate is enhanced. Chemical durability is enhanced. The interaction of the outer atoms on the surface is enhanced. So that is the first thing. And the second one is the quantum confinement. What we discussed in the previous slides, when the material is in the ordinary state, the grain sizes or the molecular sizes is in the order of microns. Whereas here it is in less than 100 nanometers. We are reducing the size by 1000 times. When we compress the interior structure by 1000 times, there is the change of the energy levels. The energy levels of the electrons in the material can be modified. Such modification of the electron states or electron levels or energy bands is known as the quantum confinement. So here, if we use nanomaterial, small size of the particles here, then this band gap is enhancing. It is extending, becoming large. Whereas when we use the bulk materials in the micron size, and it is squeezing, so the band gap is decreasing. Here, suppose if we consider the quantum dots are nothing but the semiconductor nanoparticles exhibiting the size less than 100 nanometer. We usually electronic students, they work on the quantum dots. Suppose if we consider a quantum dot of this big size, then its band gap is less. Gradually, I am decreasing the size of the quantum dot. When I am decreasing the size of the quantum dot, its color is shifting from red to violet continuously. So this is nothing but band gap engineering. Okay, band gap engineering is nothing but the quantum confinement, adjusting the energy states of the electrons in the material system. So thereby we generate the colors. Suppose if you imagine a new model LED television, then on the surface there is a glass. In such a glass, we have to arrange infinite number of transistor arrays or diode arrays, so that depending on the channel and the input signal provided to that television, that is showing streaming out one particular program. There its transistors are nano LEDs on the surface of that glass. They are adjusting their band gap. Thereby, we are enjoying the colors. Otherwise, in 1980s or even in the 1990s also, we used it to watch black and white television only. Okay. Now, this is the enhancement of the technology with the band gap engineering that is possible with the quantum confinement. Just reshuffling the or readjustment of the energy levels. And here, once if there is the extension of the surface to volume ratio, if there is modification of the energy band gap, then we see the difference in the properties of the materials. Chemical properties, increasing chemical durability, reaction rate, physical properties, reducing the size, surface morphology, structure, mechanical properties, increasing their rigidity, toughness, tensile strength, magnetic properties. If the material is non-magnetic in normal state, in the nanoscale, it is becoming like magnetic material. If already the material is magnetic, it is becoming like supermagnet. The insulator becomes conductor, conductor becomes insulator, color change, optical properties, electronic properties, band gap changing. Here, chemical, physical, mechanical properties, these can be explained with the help of the surface to volume ratio. Magnetic, electrical, optical, electronic, they can be explained with the help of the quantum confinement concept. But here there is the last property is there, no? That is the thermal properties of the materials. This can be explained with the help of both the surface to volume ratio as well as the band gap values. That means quantum confinement. Here in this, we can understand the heat transfer, phase transition, crystallization, melting point of the nanomaterials. Here, see some examples in the nature, strictly related to the thermal properties. This is the optical element in the first picture. Here you can see the broad ears of the African elephant. In African hot summers also, always its vibration rate or the movement of the ears is very, very high. That means here when we see the surface to volume ratio of this elephant, here it is big, it is very high when we compare with the body. The body is absorbing the heat energy from the surroundings, but it's the surface to
Just 1 minute, please. There is some technical question. Online.
so here right when we see the rest of the body, except the rest of the body, determine the surface to volume of the elephant and determine the surface to volume ratio of the ears of elephant only. Then here surprisingly this become high, and also depending on the conditions, it vibrates its ears continuously. That means because of this technique, it is cooling its body. The blood that is flowing through the ears that cools quickly because of higher surface to volume ratio than that of heat transferred into its body. So it can survive. And here when we see this second slide, the fire spread behavior because of extension of the surface to volume ratio. We see this is in the forest. When we see the surface to volume ratio of leaves of a tree, it is bigger than the trunks. So they fire immediately. We copy this technique also so that the automobile engineering students can prepare the nano fuel. And here in the third slide, we can see why are my hands so cold. Here the fingers, they have the higher surface to volume ratio. Thereby there is the quick transfer of heat from surroundings to the body. If the surroundings with less temperature, they absorb the heat. Likewise, here the transfer of the heat depends on the value of the surface to volume ratio. If more surface to volume ratio is there, more transfer of energy, either from body to surroundings or vice versa. Here, because of this one, we get phase transitions in the materials. We have to catch up this one. In the previous 3 slides, copied from the nature, what we have to get a point is that lowered phase transition temperatures. There is the modification of the phase transition temperatures. Let us understand them. Here we see 2 types of the reactions or processes when the material is providing heat treatment. When we heat the material, then also we can convert the ordinary material into bulk material. Sorry, bulk material into nanomaterial. There it undergoes 2 different reactions. One is endothermic, another one is the exothermic. In the endothermic reaction, the material absorbs the heat from surroundings. In exothermic, material emits the heat to the surroundings. Using this endothermic phase transitions, the material converts from one state to another state, solid to liquid. Otherwise, in the melted form of the material to a formation of the glass by supercooling manner. In the exothermic, we identify in 2 ways. One is the nucleation, that is a small heat treatment given to the material, and the second one is the crystallization, giving the high treatment given to the material. So we are going to discuss these 2 things, which are the basic concepts involved in the thermal characterization of the nanomaterials. In order to thermally characterize the materials, we have to understand endothermic reaction and exothermic. Here, this is the quartz crystal and this is the quartz glass. The difference is already my previous speakers they explained what is difference between crystal and glass. Here, this is the crystal in which regular periodicity is there. This is the glass. There is irregularity or disorderness is there. So this is the glass material. This is the crystalline material. So glass, my work is on preparation of nano glass ceramics. So glass material means first of all I have to prepare a material like this with disorderness. Later I have to convert that into glass ceramic. Ceramic means I have to make this as the crystalline solid like this. I have to convert this glass into this one. Later what I have to do? Nano glass ceramic. Again I have to do something. That means thereby I get a picture of both things in nano scale. That is in this way. First we prepare the glasses. Already my previous speakers explained about this preparation of the glasses. First we take the material in crucible and we heat it up to 1000 degrees centigrade. And then we pour on a brass mold and we anneal in a chamber at 300 degrees centigrade. Thereby we prepare the variety of the glasses. This is known as the melt quenching technique. Here, this is the preparation of the glasses at the Center for Nanoscience and Technology. Here, we have taken the appropriate amounts of the composition of the materials in mole percentage, 100 mole percentage. Dear students, those who are interested in core projects, especially in nanotechnology or material science, materials engineering, always refer 1 mole material. 1 mole material. You know the importance of 1 mole material. How many atoms are available in 1 mole? What is that number? What is that number? Avogadro number. Very good. Excellent. So Avogadro number of atoms are available. So you do research. But scientifically you have to investigate so that you consider only 1 mole material, 100 mole percentage. Suppose this is the first chemical, second chemical, third chemical. So first is 30%, second is 40%, 70 over. Again, this is 30%. Otherwise, this is 80%, this is 15%, this is 5%. Likewise, we take the composition of the material 100 mole percent. That means 1 mole material can be prepared. Then we weigh it as per the mole composition. And we grind it using a gate mortar and piston setup. And then we cool here. Sorry, we heat here up to 1000 degrees centigrade. We work on the bored glass cells. So we heat the sample up to 1000 degrees centigrade. Later we remove the melt from the furnace and we pour on the brass mold and we keep annealing in another furnace at 300 degrees centigrade. Later we get the samples like this. These are the samples, glass samples. After getting the glass samples, using this small furnace, you see this small furnace is there now. In this small furnace, we have to keep the samples for 1 hour to avoid the internal stresses inside the materials. After that, these glasses are known as the pure glasses. Pure glasses or unheated glasses. These unheated glasses can be heated in this furnace at 400 degrees centigrade usually. Okay, that is about one particular parameter known as the glass transition temperature. I will explain what is glass transition temperature. Suppose if the glass transition temperature is 400 degrees centigrade, then I have to heat these materials once again, not less than glass transition temperature or at nearly to the process of glass transition temperature. Then these glasses can be converted into glass ceramics. Glass ceramics. That is the second process. In the third process, once again, I use this big furnace. This is the big furnace. Okay. Here, there is one particular parameter known as the crystallization temperature. Say its crystallization temperature is 800 degrees centigrade. About that 800 degrees centigrade, I have to reheat my samples again here with one particular heating rate here. Okay. Then first I get this glass, later glass ceramic, later I obtain nano glass ceramic. The process is in this way. Here, what happens physically here is, after melting we get the liquid here. If we supercool the liquid, that means the sudden cooling of the liquid in the liquid state to glass state, it undergoes a particular value here, one particular transition here, known as the glass transition temperature. This particular point is known as the glass transition temperature. Otherwise, after getting the liquid, when the material is in the molten state, if you cool that slowly 1 degree centigrade for 1 minute to the room temperature, then you don't get the glass material like this. You don't get the glass material like this. You get a different material, crystalline solid, otherwise crystalline solid, and it is not transparent. And it is not transparent. So then you found the crystal. But practically these are not useful. But glasses are useful. Why? Because we have to wear spectacle glasses, glasses on the televisions, mobile phone, and so on. Glass is the important technological material. So here, this particular point at which the liquid is coming as the solid is nothing but the melting point, or solid is converting from solid state to liquid state is nothing but the melting point. In between this glass transition temperature and the melting temperature, there is a temperature known as the crystallization temperature. We will see that. In the process of creation of the fabrication of the nano glass ceramics, what we are doing, first we are synthesizing the glasses, then again we are applying the first heat treatment, converting the glass into glass ceramic. Later we are applying the second heat treatment at high temperatures, that is like nano glass ceramic. Okay, 3 steps are involved. Here we heat this first heat treatment. The temperature should be at and around glass transition temperature. The crystal, in order to get the nano glass ceramic, the heating temperature must be at and around crystallization temperature here. This is exactly identical to a routine process at our homes, that is in this way. See, when we examine their structure using the SEM, here this is the structure of the pure glass, nothing else here. Okay. Here there is formation of the nuclei. Here the nuclei means this is the not the nuclear system with the protons, neutrons, and all. It is the nuclei of or the seeds of the crystals. These are the seeds of the crystals to grow the crystal material in the glass matrix. So these are the seeds or nuclei. They are just emerging out when we heat at low temperatures. If after heating at high temperatures, we are growing the actual crystals like this. Okay. Here the concept is in this way. This is the nucleation process. This step is known as the nucleation process. Second step is known as the growth process. In the nucleation process, we seed the crystals. In the growth process, we grow the crystals. Here, its temperature is about Tc, its temperature is about Tc. And here there is one particular region that is known as the Ostwald Maris range. There, if we heat the material, then you don't get these nano rods like this. You don't get the nano rods like this. This material spoils and you get the different zigzag structure again. That is not useful for the technical purposes. So we have to meticulously characterize or synthesize the samples technically here in this way. Here you can see for this first nucleation process, we are heating the sample with a certain slope rate, heating rate, 5 degrees centigrade per minute or 10 degrees centigrade per minute. And we stay at 4 hours time or 10 hours time there only. Again, we are heating the sample with a different slope rate and we stay there for some time there. Then only we get this one. Okay. Otherwise, we don't follow this sequence. We get the different thing here. Here, this is the one particular temperature region. There we don't get the crystal growth. That is known as the Ostwald Maris temperature. Here you will see this the analogy of this process. Suppose if you want to prepare sprouts in our home, what we do first? These are the green grams. We clean them and we pack them in a wet cloth, right? That is one temperature. So this is a pure glass. Now after maintaining the same condition for the wet grams, in the morning what happens? In the morning what happens? You can see this type of growth or the seeds. You see that is the generation of something here. This is known as the nucleation in the material science. After that, if you don't eat them in the morning, what happens? After by evening or in the night, you can see this structure. That means here there biologically we are growing the material from normal state to this nanocrystalline state. Similarly, thermally we are growing the glass into glass ceramics, thereby nano glass ceramics. That is the idea what we are using in our research. And I filed a patent. Okay, the previous slide may be very simple slide for you, but I copied this concept. Just I copied this concept, and I prepared bismuth borate manganese glasses doped with zirconium nanoparticles. Their manganese and zirconium, they act as the seeds in my glass. When I heat them, they grow like a plant inside the glass network, and I get the nano rods. I will show that one. The nano rods like this. Okay, these are the particles, zirconium and the manganese particles. So we have published a patent, and we got the response also very soon that will be granted. This is the patent number. And we thermally analyze the materials with three techniques. These materials. One is the DSC, known as the differential scanning calorimetry. Another one is the TCA, thermogravimetric analysis. One more is the differential thermal analysis, DTA. Here, the basic principle in the TGA, when we see this TGA, here just we measure the weight of the sample as a function of the temperature. In differential scanning calorimetry, we get the difference of the heat flow in the sample and the reference point. Here, in case of the DTA, we get the difference of the temperatures of the sample and the reference point. These are the basic principles. This is the equipment of DSC. Here you can see a sample material here, and this is the crucible in which we keep reference material. Sometimes we keep it as empty, and we heat both the crucibles with the uniform heat rate and maintaining the same temperatures by using individual furnaces, so that the material undergoes phase transitions. Okay, that will absorb the heat energy at that is becoming like a glass material. That is known as the glass transition temperature. And when it is converting like crystalline solid, and it emits the heat energy, that is the exothermic reaction. Again, it melts at high temperatures, known as the endothermic reaction. So we get that data using a laptop or a system. That means here we measure the heat flow or heat transfer as a function of temperature or time here. Here we get just measure the amount of heat difference between the reference crucible and the sample crucible. Here this is the schematic of the DTA. Here also we use two crucibles. This is reference and this is the sample. Here we use only one furnace. One furnace can supply the heat, but the sample absorbs or re-emits the heat when we compare with the reference. So that the difference of they maintain at two different temperatures. That difference of temperatures can be taken as the output, and we plot a graph using the computer. That is known as the DTA analysis. Here in the DTA, just it is in terms of the difference of temperatures in the previous heat flow. And this is the schematic of the TCA, gravimetric analysis. Here we use a furnace, and we keep a pan, weighing pan. We put the sample in the pan, and we weigh it as a function of heat treatment. Suppose if I prepare a glass sample or ceramic sample, because of these weather conditions that absorbs the moisture in the atmosphere, so its weight is more now. Now, when I keep my sample in this pan and start heating, then what happens? The water molecules in the sample, they can be evaporated out. what happens? The weight decreases or increasing? Decreases or increases? Weight, the water in the content is evaporating here. The weight increases or decreases? Decreases. That's what we measure. That's it. That is the thing. Okay. The mass of the substance is continuously monitored as a function of the temperature. Here, these are the differences. TCA is known as the thermobalance. DTA is known as the DTA apparatus. DS is known as the calorimeter. Here, mass versus temperature or mass versus time is taken. Here, difference of temperature versus temperature or time is also taken. Here, this is the heat flow. That means heat energy per second versus temperature or time is also measured. Here, some limitations on TCA. Both DSC and DTA can give more thermal information, but TCA cannot provide that. That is the limitation. Here, coming to our study now. After preparing the nano glass ceramics, in the first stage we prepare the glasses, right? After preparing the glasses, as Thirumal sir said, the fingerprint of glass characteristic is the X-ray diffraction. We get the X-ray diffraction like this, okay? So, if I get the X-ray diffraction like this, here I can see a broad halo, and I can see another short halo here. So, if I get two halos, then only I can seed either manganese or zirconium in the glass network. Then only I grow the nano rods, okay, nano flowers, nano particles inside the material. Otherwise, I cannot grow them. Suppose soil is there, good. If soil is there, good soil is there. If we throw the sprouts on the good soil, they grow. But if we throw them on the tar road, what happens? They don't grow. Similarly, here also, after preparation of the samples, if we get the X-ray diffraction, when we get these two halos, then only they are ready to grow the crystalline solids, crystals in the material. So after that, we heat the material. When we heat the material, gradually they are showing the peaks. These sharp peaks, they show the crystalline nature of the nano glass ceramic. Here, initially for pure samples also we have tested at different concentrations. Here you can see the clear broad halo and the short halo. Here this is due to the short range periodicity. This is due to the medium range periodicity. In some of the materials, there may be one more halo that is known as the long range periodicity. Then we can create new models of the nanomaterials. Here coming to DSC analysis, here this is the DSC curve. You see the heat flow is like this. Here it is going down. It is going down means the sample is absorbing the energy. Sample is absorbing the energy means endothermic reaction. This endothermic reaction shows the glass transition temperature. This is the glass transition temperature for the undoped sample. This is the glass transition temperature for the nickel oxide doped sample. And this is the, after that, at the high temperatures, there is the peak like this. This is related to the crystalline temperature at the high temperatures. This is the exothermic reaction. So here, this is undoped sample, this is doped sample. When we heat it, when we trace the DSC traces, then there is a shift of the crystallization temperature from 694 degrees centigrade to 685 degrees centigrade. That means the temperatures are coming towards the lower values. That happens in the nanoscale. And in some of the materials reported by other scientists, here depending on the X-ray diffraction, if you are getting 2 halos, 3 halos, 1 halo, you may get multiple crystallization points also. This is the glass transition temperature at 450 degrees centigrade. This is the first crystallization temperature. This is the second crystallization temperature. This is the third crystallization temperature. This happens in the glass ceramics. Here, this is the DSC curve of amorphous polymer. You can see this is the glass transition temperature. And first there is a small kink here. Okay, and there is a sharp kink here. then this type of the crystallization temperature is known as the cold crystallization temperature. If the crystallization temperatures are not clearly resolved, then we call the amorphous solid is exhibiting the cold crystallization or silent crystallization here. And this is the melting point that is showing by the endothermic reaction. And here in the different glass particles in the size of silica mixture, here its crystallization temperature is like this, and its grain size is decreased in the texture manner. It is decreased further. Again, it is in the order of micro or nano. It is again decreased. So there is a shift of the glass transition temperature or crystallization temperature towards the stronger values that happens in the nanomaterials only. Here, this is another example of DSC curves represented by some mechanical engineering researchers. You can see this is the glass transition temperature of different samples. They got two different crystallization temperatures, TC1 and TC2. And rising the crystallization temperature gradually, they observed that micro hardness is increased. Micro hardness is increased. And their bending strength is also increased. So that when they grow the nano wires using such materials, then their bending strength is very high. Here, this is a different curve. Here you can see heat flow on this x-axis and temperature on y-axis. Here it is the integral of DSC response. Integral of DSC response means actually what we take on the x-axis means heat flow. It is in terms of watt per gram. Watt per gram. Okay, joule per second per gram of the material. When we integrate the power, what do you get? What is the integral of power? Integral of power. Energy, very good. So here we can determine the energy. This is the curve that is showing. If you determine the area under this peak, the area under this peak after getting the line integral, then you get the energy required to make a crystalline solid or to make the glass transition. And this is another response of the iron nickel magnetic nanocrystal, where there is the shift of the crystallization temperature. And here we use a particular parameter known as the Cook-Bees parameter. Usually the glass scientists refer this parameter, KCl. Here it is its formula is Tc minus Tc by Tm minus Tc. Tc is crystallization temperature, Tc is the glass transition temperature, Tm is the melting temperature, Tc is the crystallization temperature. Tc, this is Tc, and this is the Tm. Substituting there, we get the parameter value. If parameter is high, if the parameter is high for the given set of samples, that shows that more packing fraction is there, more bridging oxygens are there, more oxygen packing density is there, more toughness or rigidity comes to the nanocrystal. Here we correlate the same data with the dielectric properties also. Here this is known as the pole plot. Here along x-axis we take the dielectric constant, whereas y-axis it is the product of dielectric constant and loss. So here we get this tangent value, which is known as the beta pi by 2. Thereby we determine beta. If this beta is more, lower packing fraction, lower packing fraction, more non-bridging oxygens, lower OPD, oxygen packing fraction, low rigidity. And this is the TCA analysis. The temperature is given and the response of the weight of the sample is taken. It is gradually decreasing. After a certain point, it is going down immediately. Okay. You can see a steeper line here. This the steeper apex starting is known as the first decomposition temperature. Second one is known as the second decomposition temperature. Usually, this is very close to the glass transition temperature, whereas this is very close to the crystallization temperature. And these are the nano rods developed at NIT Warangal with the collaboration with Professor Dr. Dapparao sir. This is the pure PLA, polylactic acid film, biofilm it is. We get the structure like this. After adding ZNO, we get the situation like this. We see the ZNO granules here. Later, heating that ZNO, we have grown the nano rods like this. Okay. And we got the thermal characterization in terms of the DSC and TGA also. And coming to applications, I just run through the slides. They are usually used in the industrial, commercial, and domestic purposes. Here you can see the glass ceramic, which is used to fabricate the chest pieces. Here you can see the glass ceramic used to grow the teeth crowns. Here in 3D printing technology also for the mechanical engineering students, you can fabricate the dental restoring devices or bone grafting materials. Here, in order to do some replacements in the ankles, knees, we make use of the bio nano glass ceramic materials. And here the applications of nucleation method. Why should we consider this method only particularly? This is useful for the electronics engineering students. Homogeneous means suppose if you dope one element only in the glass system, for example, manganese or chromium, then that is known as the homogeneous nucleation. If you dope two materials, suppose zirconium and chromium, then that is known as the heterogeneous. In the homogeneous, the glass materials can be used for the direct wave guides, fiber, optical fibers, fiber amplifiers, etc. Whereas in the heterogeneous manner, we can prepare solid state lasers, warm white LEDs, etc. This is the schematic of the heterogeneous in-gas laser. You can see the LEDs here. And this is the hydrophobic nano coating products on the surfaces of aeroplanes, cars. Yeah, before coating, there is the glaring of the surface with light. When the coating is applied with nano fluid, then there is no glaring, no scratches, no rust, no fade out. And for electronics engineering and CSE students must follow this application. AI-based wearable electronic devices, GPS sensor in a mobile phone, smart goggles, watches, rings, and so on. And the conclusion and the takeaways are like this. We can prepare the nano glass ceramics with the nucleation and the crystal growth technique. And here the structure can be controlled using the parameters, glass transition temperature, crystallization temperature, and melting temperatures. All the thermal characterization is helpful to understand any property of the material. And here we can get some applications in our daily life in terms of the photonic applications, 3D printing applications, AI-based electronic devices. Thank you, Arvind.
Thank you very much, sir. Now it's time for the questions. If you have any questions, please come forward. Sir, question?
Informative talk, sir. I have small questions. While we go for the nano scale, what could be the origin shuffling of energy levels, changing of the band cap of the levels? Could you explain some understanding?
This one, sir.
Yes.
The see, this is the material with the larger size. Gradually, the size is decreasing. Size is decreasing means there is the migration of the particles from interior of the material to the surfaces. Okay, so the grain size is decreasing. The particle size is decreasing. When particle size is decreasing, there is the shuffling or rearrangement of the electronic levels depending on the transition of the material from normal state to nano state. This is not necessarily the blue shifting. Sometimes that may happen red shift also, depending on the material composition. The process what we apply there, I have applied the heat treatment. Sometimes somebody they apply the shock treatment, electric shock treatment. In that process, there is making of creation of new bonds or new electronic states. There is the change of actually density of states. That can be explained with the help of one effect known as the mass bursting effect actually. With that mass bursting effect, the density of electronic states modified as a function of the input energy accepted by the molecules or atoms. So that if we consider chromium, Cr2O3, Cr3 plus ion is there. So in such a Cr3 plus ion, depending on the host glass matrix or host material, not a glass, for example, that may be a polymer also. It can give additional energy levels depending on the surrounding crystal field. We have to say here crystal fields. In presence of the external electric field or crystal field inside the material system, there may be the losing of electrons, absorbing of electrons, addition of electrons, deletion of electrons, bridging of oxygens or non-bridging of oxygens. So in that process, there is the modification in the energy levels. If there is a modification in the energy levels, the copper level, that is valency level, that may be accommodated with less than 4 electrons. Less than 4 electrons. Then that shows the conductor properties, conductivity. 4 electrons only, semiconductor. More than 4 electrons, insulating. That is the thing, there is the electronic modification. Electronic or electron transfer into the interior shells, which is nothing but the quantum confinement. I hope you understand.
Thank you for the question, sir. Any other questions? Please come forward. So if no questions, so I can conclude the session. So in summary, started. Yeah. So this started with introduction to nanomaterials and how nanomaterials are biomimic. They be this biomimic may influence the learners in the direction to do the work. The importance of surface to volume ratio and quantum confinement. And sir also discussed endothermic and exothermic reactions and showed the work which has done in the nanoscience Center for Nanoscience and Technology at VNRVJIET. Along with that, the sir also showed the thermal characterization to do the glass transition temperature. And it's nice to see the similarity between the sprouts and the nano glass formation. So, and the differences between the DSC, TJ, and DTA, all these things were explained by sir very well. Thank you from the organizers once again, sir. Thank you very much. Now it's time to move for the next session. I think the last session for the day that was on the nanomechanical characterization of materials. And this session was explained by Dr. G. Suresh. And Dr. G. Suresh sir has completed his UG in the year 2002, that's MSc Computational Physics in 2007 from Osmania University, and MTech in Mineral Exploration Geophysics in 2010 from University of Hyderabad. He worked for quite some time as a geophysicist at one of the prestigious CSIR laboratories. AGRI, as an explorer in seismologist. Later, he moved to IIT Madras to pursue his PhD in the year 2012. He published several research papers in experimental soft condensed matter in several international journals obtained many awards for his research works and best presentation in his academic career. He is a member IEEE Hydroid section. His areas of research interests are experimental condensed and soft condensed matter, polymer nanocomposites, energy harvesting materials, soft robotics, sensors, and actuators. He has 3 years of teaching experience and is currently working as an assistant professor in the Department of Humanities and Sciences at VNRVJIET Institute of Engineering and Technology, Hyderabad, India. Now we request the sir to take the session. Sir, please.
Thank you, Ananda. Before I talk, I have two things to say. Usually, this talk is prepared for students. Luckily, it's prepared for students. Unluckily, nobody is there to see that. So that's the first point. Second point is that actually there is a saying, you always stand upon the shoulders of the giants to look forward. Same is the case with us. I'm really fortunate enough because many of our previous speakers have already said what I'm supposed to say. Hence, it's my path is very, very clear, and I'm very freely I can move and I can just talk about it. So with that, let me very quickly complete this discussion. It's a very fundamental thing, very, very basic thing, keeping the student's perspective. The title is Nanomechanical Characterization of Materials. Here, already all the speakers have already introduced what is nano and what is nanotechnology. All these things are already covered. Now, first and foremost question is whether really do we need to look for the characterization that to at nano level? That's what the first question is. I'm not sure. Okay, let's go and explore. If it is essential, then we'll really go and see and appreciate that. So, yeah. My talk is just, I'm going to introduce why we need to understand the mechanical characterizations at nano level. That is the first point. Then I'll try to convince you, yes, it's essential to understand that at very nano level. Then I will be going to discuss about how we are going to perform that using nano indentation or nano scratch in the next few slides. Then I will wind up my talk just by saying the conclusions. This is how my approach is, and going to the mechanical characterizations and what are the mechanical responses that we incur when we see or when we explore materials at the nanoscale. But prior to that, let's ask the first question: what are the mechanical characterizations? So let me impose a question. If you are given a rubber band and a steel rod or maybe steel wire, which is more elastic? Rubber band is more elastic. Is it? Steel is more elastic. That's what our perception is different, but conventional way what we say in our day-to-day life is rubber band is elastic, we say, but it's not like that. It's our conventional saying, but in mechanics point of view, which is more what I can say rigid to withstand for applied load, that is said to be more elastic, right? If I want to deform 1 millimeter a material, maybe a rubber band, is it harder for that, or to display or to cause a deviation of 1 millimeter in steel rod, which is going to resist more? Which is going to resist more? Steel. Hence, steel is more elastic than rubber band. So these are all very, very fundamentals. So let me ask you another question, saying that suppose if I want to construct maybe a structure, and if you are given a piece of maybe the steel rods or maybe pieces of aluminum, whom would you prefer to take to construct that? Just I'm asking it Don't give the answer, but you think of yourself. Usually we go for the steel rods. Why? Why is that? Because of their higher modulus value, elastic modulus. Not only that, there are many things. Their strength is more. Their they can sustain for their yield strength is lot. So lots of, apart from the cost, there are several factors that are going to determine why we go for the for choosing the steel rods. Now, let me ask another question. Why this is steel is playing that much role in the construction industry? Because the very basic thing is that compared with aluminum, this iron can be engineered or it can be tailored as per our desire. So this is much more useful in industrial as well as application point of view. Hence, we prefer for that. Maybe you can just see here itself. These are TMT bars. TMT. They are proved over them. Why? Because in order to have a strong friction with the concrete, compared with aluminum, concrete is going to have a lot of adhesiveness with the concrete itself. There are many features, but why I'm stressing on this point, because you can engineer it just by controlling some conditions, maybe the synthesis conditions or maybe heat treatment techniques, so that you can really tailor the required properties. That's what the beauty is. Hence, this is one such point. And if you if you look for its stress strain curve, then you'll understand what is the slope. From this slope, what you can see is always steel is preferable than the aluminum. And this is at macroscopic level. This is at macroscopic level. At microscopic level, if you go and see, because macroscopic entities are nothing but they are the replica of what is happening at the very minute level, which is at the nano level. Hence, whatever you are observing here is equally applicable at the nanoscale also. Hence, and with this slide, what I wanted to say is what you are seeing at the macroscopic level can be seen at the microscope level also. How? We'll see in the next few slides. Yes, this is one more application. Why I wanted to show this is because I wanted to just convince you that really it tends very interest to understand at the nanoscale to attain or to tailor the properties at macroscopic level. What is this? It's a pair of gloves, and it's very flexible, right? Let me show another thing. This is, of course, it's also made of plastic. It's also made of plastic, but which can sustain a lot of other weights comparatively. Of course, this is plastic, and this is also, for a layman, both of them are plastic. But this plastic is absolutely different properties than the properties that this material possesses. What is the difference between these two? Let me not really discuss too many things. Here you see, if you see their mechanical property, here something like what our physical perceptions is like modulus. This is modulus, and this is with respect to temperature. At room temperature, what you can see here is this polybutylene, which is natural rubber, and this is what the property of this polystyrene, and it's a synthetic material. Here, what you can see is the temperature, which is room temperature here. Here, at room temperature, if I take a pair of gloves of this and this material, at room temperature, this polyisobutylene, which is in the glassy state, because you see, at higher temperature, its glass transition is already crossed. Now it's in glassy state. Now, whereas at that particular temperature, at room temperature, this material is still in its it's not in the glassy state. Here, what I wanted to convey is, once if you understand its mechanical properties, then you can really tailor its physical properties, like its applications, where it is going to be useful by understanding its mechanical properties. And I can go on telling about this, but for the timing, I hope you understood it. Why it is glassy, why it is tough. this is tough and why it is so flexible at room temperature, right? So which says that if you want to really engineer these materials, you can play at the very atomic level or microscopic level by controlling their interatomic interactions. So to appreciate that, I played this slide. One more slide. If you look for nowadays, so many, I mean, without mobile, we can't even survive. So lots of applications nowadays coming into the market. You can see more and more applications. You can see new companies are coming up with new ideas such as the more flexible mobile phones and more capacitive, more what I can say, more feature, more kinds of different displays. Now OLED, maybe dark LEDs, these LEDs, so many different types of applications are coming nowadays. Now, if you see, if the screen itself of the mobile consists of many coatings, right? Here, each and what I can say, there are many tens of bunches of coatings are there, each having its own characteristic property. Maybe this one is having particular anti-reflective coating. Maybe the other one is going to have better sensitivity. Maybe the other one must be having hydrophobic property. Maybe the other glass may be the toughened glass. So many coatings are there. If you see, so many sandwiched layers are there. Each has its own property, such as shock-proof or impact-proof coating, or maybe hydrophilic or hydro. If you want to not to wet your mobile phone, you need to coat with antiphobic, hydrophobic coatings. So many coatings are over them. If you see it, the microscopic or even the nanoscopic level, in order to attain them, you need to incur or you need to conquer some of the techniques to lay such very thin layers. How do you engineer them? Because at that nanoscale, the properties what we see are absolutely different than what really we see in our day-to-day life. That is what the people, all the speakers have been telling about till now. Now, if you see the arrangement of these structures, so orderly, so thin, then which gives us all the amenities such as being so thin, having so tough, having so hydrophobic, having many other features, which enables this gadget more powerful than other things. Hence, since this is what running in the market, hence I thought to convince you that in order to conquer all these difficulties, you need to really master the technique to understand at the nanoscale, as well as you need to characterize really whether you attain the delivered or you attain the desired property at that particular scale. With these few slides, I just wanted to convince you that yes, you need to understand the properties at nanoscale level to characterize them, especially these mechanical properties are very essential in order to achieve the required output properties. Now, let me show you, let me tell take home point. First point is that at higher loads or at macroscopic scale, the penetration depths are more. Penetration in the sense, if you want to test the material, you need to apply lots of force, lot of what I can say stress over the substance, which sometimes really gives the bulk property of the material. But at very small length scale, at lower depths or at very lower dimensions, you need to look where really you wanted to look for, right? If you are already prepared a particle, since already previous speakers have said different synthesis techniques such as maybe solder technique or maybe some other technique, maybe some other technique, maybe PVD or CVD. You prepare a sample whose grain size is say 10 nanometers, and if you are testing with a tester whose dimension is of micron, then there is no point, right? Hence, if you have if you have a sample or if you have a material whose dimension is of small, then you need to test it with the appropriate or the smaller instrument also. This is what the next point. And what you can see is that that particular length scale, the force what you apply is may not be as equal to as that of what we applied at the larger length scale. Means the stress fields or the strain distribution are going to be absolutely different than in the macroscopic scale. Thus, we need to accurately apply and measure the very minute forces and very small deviations or deformations, which enables to characterize a material at that nanoscale. Hence, nanomechanical characterization is very essential. I hope with this you convinced it's essential to understand nanomechanical properties at that length scale. Now, how you are going to test it, characterize it, analyze it? It's very simple technique. You all know about it, but let me to have a clear idea. I just introduced the piezo force microscopy or the atomic force microscopy, where you have a cantilever, where here you can see it's very clear. A cantilever is landed over a tested sample. Then you are going to apply a certain load, or usually this load is applied by applying a bias voltage, which enables the interaction between the given material and the tip. Usually it's so close. At that proximity, what it happens is the interactions, whatever are going to happen, are usually of van der Waals kind of interactions. So no need to go for that atomic level, what interaction they are going to play. What we understand is it's going to just, it's a kind of a blind person is trying to understand what really a material is. It's a simple analogy. Hence, in order to understand that material, you just touch, you press it, or you sometimes, if you want to understand it, you try to shake it. It's a kind of same analogy. Hence, with this, I think it's no need to tell how it works. What we do is we apply a certain signal overlaid with the AC current. Usually it drives with a DC over which a AC signal is going to drive. Then that bias is going to have the interaction with the sample. Then in response, the material is going to respond. If you apply more force, then it's going to have interaction with that. When you are applying lesser or in opposite direction, if you apply the voltage, it's going to pull it. So the material may not exactly in sync with the signal what you really apply. There can be always some phase difference between the signal what you apply and its response. There can be a lag. That phase difference and its amplitude we are going to measure to get the that signal what we analyze. That I can show you as a simple graphic. You can see here the tip is driving over the sample where the polarizations are oriented in different manner. Here somewhere standing up, the next is flipped down, standing up and down like that. The signal what we apply and how its response is, that's what you are going to continuously measure. That's why all these instruments are called continuously measuring indentation techniques, or continuously measuring uh, mechanical characterization techniques. See, not only touching, you are trying to shake it, or you wanted to understand how its response is, whether it's really stiff or whether it's really flexible. Sorry. So this is what I think, yeah. With respect to time, with respect to space, with respect to frequency, with respect to temperature, many variables you can control to attain desired outcomes from this measurement. I hope Fine. Then we'll go to the next. Yeah. With this technique, it's analogous. We are going to use this principle to really understand the mechanical properties of a given sample. How? There is a technique called nano indentation. Nano, indentation. Indent means you are going to press or you are going to apply a certain load and you are going to see how its response is. That's what indentation is. How you are going to see? As I said just now, the piezoelectric mechanism runs behind, which drives here the indenter. Indenter is a very, very, very small tip where you are going to apply a certain load or a given sample. You see here, there is an indenter tip which drives into the system or to the sample, which left an impression of its shape. Right. So what really we are going to get? Usually you are going to load you are going to apply some load on a sample. That means you are applying some load or force. Then the material is going to get displayed. This is what you are going to measure. Means a force and how it's a response. These two things you are going to measure. Yes. There you can see with respect to this is what the depth of penetration. Here, how much depth our indenter is moved into the sample. That is what this depth on x-axis. On y-axis, I have taken how much force I really applied. How much force I applied on y-axis, how much depth of penetration it went. That is what P versus H I'm drawing. If you see, initially, isn't it? When we try to apply certain load on the sample, initially it resists its penetration. So that's where every material try to resist its physical deformation. This is what in fact called the hardness of the material, right? Hardness is the resistance to physical, physical deformation. So initially, we all know Hooke's law. Up to certain level, it follows the linear. Then it is not going to be no more linear. Then you apply whatever the force you wanted to apply. And if you want to understand its creep behavior, creep in the sense you apply a certain load, keep there for a longer time, and see whether the deformation is still happening. That's what the creep. If you want to test for creep, you can have the creep test, or simply you can just from here itself release the load. That means apply the force, I release it. Hence, you are retracing the indenter. At that point, what it happens is the material tries to regain its original shape. Initially, at the very beginning, when you are trying to withdraw the tip, there it's trying to again behave elastically. As time goes, when you completely remove the force, it's going to somewhere end up here. Why it is ended up here? Why it is ended up here? I expect when I apply a force and I release it, as it's supposed to come back here, no? It's not coming here because of the plastic nature of the any material. Any material is perfectly not elastic, nor it's perfectly plastic. It's somewhere like elastoplastic in nature. Every material, even you take any material, so it's not going to be perfectly no elastic, no plastic. Hence, there will be always a result. What I can say the remnant displacement within the material. That is what it's giving. Now, from this load versus depth plots, what I get? Let us see. As I said, at the very retracing level, or when you are removing the force, then this tangent or the slope of this is going to give you the stiffness. That's what I showed here. Stiffness is simply the slope of P versus H. This is going to be the stiffness of the material. Hence, I can find out how hard or how soft that material is by understanding this pH curves. So, and these are the formulae. You can see here, H is the hardness. From this plot, what I can get is the hardness of the material is given by the maximum load what I apply. If I know what load I apply, because I know what load I can apply, or what is the maximum load I apply. With that, And what is AC? AC is nothing but the contact area. You see, here it left impression. No, that area of contact we can determine it. We can determine it. Usually we fit with the fit parameters to obtain this area of contact. How we get? Area of contact is obtained by how much depth of penetration it went into. If you know that depth, this you don't know, this you know up to what depth it went. Using this, there is a relation between area of contact as well as depth of penetration. Usually it follows the higher order powers of HC. HC means this maximum depth. Hence, you can always find out area of contact. You have the maximum load, then you can find out the hardness. And ER is given by under root pi by 2 beta into S by under root AC. So what it is trying to convey us is, I measured its modulus. Modulus is simply the slope of stress to strain graph. How much elongation it took and how much is the load I applied. The slope is going to be given by modulus. So, and here it's called the ER, reduced modulus, because it's not real modulus, it's a reduced modulus, because the tip itself is sometimes going to undergo some kind of deformation. Taking that into the account, we always measure reduced modulus. It's not true modulus. But still, this modulus really happens just because of the, just now we were discussing, the previous speaker was saying about why deformations are going to take place. If I apply some load or some force, what it try to do is at the very atomic level, it try to deform the bonds whatever exist in between two atoms. Suppose that force is sufficient enough to really depart them, you are going to get the rupturing of the bond. Hence, you are going to make it the damage to the material, or you can give a permanent breakage to the sample. Else, when you apply a certain load, it simply deforms and you try to regain its original position. That's what elastic in nature. So this is what all can be depicted in this modulus. Also, you can get the hardness. Hardness is usually, it can be engineered, but it's inherent property. I hope I try to convince how we are going to measure this modulus values and hardness using nano indentation. Then, if you let me give some examples where really we apply on how we are going to apply this indentation technique to understand the nature of given material. See here, this is a material upon which try to apply some load. This is the tip. This direction shows the force direction or the load direction. Then you try to deform the material. Whose impressions? Leftover impressions I can see here. Right? Looks good. This is what called indentation. It's not always just we apply a force. Sometimes if you want to really understand what is happening interior to the sample, you can still go into the deeper of the sample to understand what it is or how it's responsive. That can be done using scratch technique. Scratch is simple. How we scratch? We apply a load, but tangentially we draw the load so that it try to penetrate into the sample and it try to pull off the material. Now you see what you can see here is, yeah, here a load is applied. Now you see the load is in this direction. Tangent of force is trying to pull it. Hence, as time goes, it's going to go deeper and deeper to understand what really interior is made of. You can see here, if the material is really heterogeneous in nature, it's not uniform. If it has different materials that are overlaid within, then you can see different stacks of those that response here. Or if you want to understand there is a spatial inhomogeneity on the surface itself, but that also still you can see using the scratch technology test. Not only these two, we can even do impact test. Impact test, just now as I said, the surface of a mobile phone can be, earlier there used to be simple glass. Now the technology has gone to Gorilla Glass, so now new technology has come. How they are improving it? At the very nano scale, what they do is they try to prepare the sample, because already glass experts are here. Those who already said how they prepare the glass. Now, in order to strengthen this glass, what they do, other than conventional way of maybe putting a sodium atom, I replace it with maybe potassium atom, maybe even a bigger atom, maybe just someone said like zirconium or maybe some other element. So if I try to impede a bigger system, then it's very difficult for it to come out of that system, right? It's amorphous in nature. It doesn't really try to come out. Even if you try to pull it off, it can't because of its own rigidity. Hence, that's how bigger and bigger new technologies are coming to give stronger and stronger toughened glasses and all. So one such example is the Gorilla Glass. If you want to crush any material, you wanted to understand its strength. So usually impact, yes, impact is nothing but it's an impulse. Lot of force in no time. That's what impact is. So you can test, you see, repeatedly, force is being applied to the sample to understand up to what level it can withstand for that impact. So such a test can be done. And also you can even do some wear tests in order to understand because repeatedly some whatever the materials we suppose if any automobile spare part is there, it is usually subjected to several repeated cycles. It undergoes so many kinds of what is called loads. Then what it happens as time goes, slowly it can get degrade, right? So in order to understand up to what extent it got damaged, you need to understand the wear nature of that particular material. Usually nowadays, all the bearings, all the types of frictional, wherever tribology is coming into picture, these give this nanotechnology coming into picture to coat with very, very thin layers. So up to that extent, whether it is being coated, after coating, whether it's really doing whatever required stuff. So in order to test them, you need to do the wear test. In wear test, what we are doing is simply, I'm sorry. So what we are doing here is you are applying a load and you are scratching simply like scratching is a longer process and here it's a local process. You keep on applying some load and you are just trying to just rubbing and saying like. So with all these techniques, these are the different types of techniques that are incurred in nanomechanics to understand the property of given material. Then at this point, again, I wanted to convince you because in the earlier slide, what I said is it's very essential to understand the properties of a nanoscale. Hence, just now I said different properties with varying loads, with varying time, with respect to different frequencies of applied force, with what rate you are applying the force. All these things are going to vary the property of the material. Hence, it's very, very essential to understand the dynamics of the given material because so many things are dynamically varying. Forces what we apply, at what rate you are applying, at what temperature you are applying, at what frequency you are studying there. So many parameters are there. Hence, this is also very essential to understand. Hence, with that, I feel like I just go into the real characterization. One such an example I'm showing just now, I displayed a material is being taken and try to understand how its mechanical response at room temperature. I said dynamic, no, how dynamic, let us see. So at room temperature, taken the sample and try to apply the force and see the nano indentation. Now what I try to do is, I try to increase the temperature of this sample, then I'll try to see what it happens. Yes. Now it's being taken to elevated temperature. It's at room temperature. Initial one is room temperature. Now I took it to a certain 100 degrees Celsius, 80 degrees Celsius it is. Then if I take it to further temperature, larger temperature, around 130 degrees Celsius. Usually this is a polymer. Polymers cannot sustain for longer temperatures, but hence here what we did is we have taken the polymer sample to understand what happens this material at the nanoscale by varying its temperature, dynamic process. Now, after taking it to the elevated temperature, it's already been melted now. Now we are trying to recrystallize it. Now you see here, it's been recrystallized. Now you see the morphology is absolutely different than what it used to be earlier. Now you can see many things you can observe. If you keep on talking, 1 hour goes to understand this itself. But you just see as time goes, the smaller impressions became bigger. Why? All of them are in the same scale. This is say if it is 20 micron, This is also 20 micron and this is also 20 micron. But what I can see here is the impressions got bigger and bigger and bigger. So what does it indicate is bigger impression or bigger area of contact means its plastic nature has come into the picture. Earlier at room temperature is hard. Now as the temperature is increased, it became softer. It's displaying more and more. Hence you are getting more and more impression. So this is what this recrystallization process has gone from here to here. Then all this process from room temperature to heated to certain temperature to higher temperature, then it's completely melted. Its melting temperature is somewhere 200 degrees Celsius. We can't really take at 200 degrees Celsius since it's in the liquid phase. You can't really touch the sample with the tip. It has its own limitations. Hence, now it's recrystallized. Now you see, as it's recrystallizing, its morphology got, of course, not too much difference, but still its morphology is absolutely changed. Now, to understand what happened at this, see, now I can show load displacement. This is at room temperature for the initial sample, applied some load and taken off that load. Looks good. Then at higher temperature, applied same load, retract. Then at further higher temperature, heated and brought back. After that, the material got recrystallized. It is at while cooling, this is what? Then it is at the intermediate stage, and finally it's recrystallized. Now, if we analyze lots of things we can find, but very pointedly what I can say here is, what I can see is its depth of penetration is what initially is now also seen the same way. But as it is varying from temperature is varying from room temperature to higher temperatures, what I can say is its width as well as its depth of penetration. Depth of penetration in the sense we are applying more same load, but the creep nature is coming into picture here. And also what you can see is their areas are different. Different areas means if I draw a line like that, so this is what the recovered part. This is what the recovered part and this is what the unrecovered part. That means there are two types of things are running here. One is plastic nature, one is elastic nature. That I'll show in the next slide. But for the time being, I hope you can understand at least just by not by quantitatively, at least qualitatively, you can see lots of things you can get from this. Now, this is what after analysis you can find out before melting, sample's hardness is this. After recrystallization, again, how much its hardness is. Of course, not too much difference, but still you can see considerable amount of difference. So if a sample is being treated with the different temperatures, with the different ingredients, and with the different dynamic conditions, with what rate, with what load, with what maximum load, these things, if you keep on changing, definitely the properties will be no more same. Hence, it's a good technique to really understand or play with these parameters. Then you see, as I said, there are two pictures here, and there are two things here. One is the plastic. This is what completely plastic. It's unrecovered, and this is what already recovered part. Hence, it's elastic. How much energy is being? This is what you can see here. How much energy area under this curve is going to be the total energy spent for plastic as well as elastic deformations. This you can always differentiate it. You can just make a separation of these two things to understand here. Now, in this slide, what I am showing here is you can see two different phases. Though it looks same material, but there are different types of ingredients are there at very nano scale. Then, if you want to understand, we just assume here there is a banana and here is an apple, whose sizes are very, very small. If you want to understand its response, you need to exactly put the indent exactly over the apple, and you need to exactly put over the maybe other banana. Hence, generally you'll understand what their independent physical response is. That's what we are going to try to understand. What we did is two different phases were prepared. We try to understand what is its nature and what is its nature. What is its elastic energy and what is its plastic energy. Not really too much into that. Then what you can understand from this is you can see alpha phase has this much hardness, whereas the beta phase has lesser phase. In fact, this is for the first time is shown that alpha phase is going to be what is that? Yeah, beta phase is going to be softer than alpha phase. And using nano scratch test, we have done same to alpha and beta phases. You see here, as I said, it is a scratch. In this scratch, this is alpha phase, and this is two independent phases were prepared. You see, a certain load is being applied, then you try to drag it, just as like a farmer. Put the plow, pull it, check it. Hence, you see here, after applying a certain load, alpha phase is only material is displayed up to 800 nanometers only for a given load. Whereas, same load if I applied on this particular beta phase, it went to probably some 200 to 300 more nanometers depth. Hence, beta phase is softer. That's what I said in the earlier case. And what you can see here is why it is so can be explained. We try to understand why it is happening so. Because in the alpha phase, where these bigger structures or micro structures are called spherulites, or some physical structure where it's something like polymer chains are so extended or elongated like that. In between them, in the interpolymer chains, some amorphous regions are there, which are responsible for the plastic nature of the given material. So if it is bigger, if the structure is bigger, when you indent, it's going to exert most of the time it is going to indent over this particular region to get the alpha nature. Whereas if the sample is like in this case beta phase, what is happening is microstructures are very, very small. Now, if the indenter is seeing this region where most of the amorphous, right, the probability of falling the indenter in the amorphous region is more in this case rather than here. Hence, in order to understand why this response has come, we propose a mechanism. Probably this could be the reason. So, at the microstructures, if you control the property, macroscopically, you can control the property. That's what I can show here. What I said can be shown here. And same thing, if several indents were done, just I skip this. And apart from that, as I said, not a single, suppose if you have a bunch of layers, it's something like that, layer over the layer, layer over the layer. In that case, also, you can independently see what is their mechanical response at first layer, second layer, or maybe the beneath layer. How? We just see a particular load is being applied. You see, load is applied up to certain depth, it went. Now, this is what untreated, means unmodified. Up to this level, it's okay. Then all of a sudden, there is a change in its slope, which says that now the indenter went to the beneath layer. Hence, there is a change like that. You can study. Even you can go into the so many. If you have a number of layers, you can go and see independent layers. Now, to strengthen that coating, modify using chemical treatments and all. It's treated. Now you see, after the treatment, it's now you see, its depth of penetration is 100 nanometers. I mean, in order to attain 100 nanometers, you need to apply different load. You see, there is a kink here. Now, its complete property is being changed after proper chemical treatment. Means you can understand what you have done is really mapped here. You can see physical thing, what you have prepared. You can test it using this particular technique. So, okay, many things you can find out here also. This is yeah, you can find out many things like crack propagation, how it happens by a given load, how the cracks are formed, and also you can do cohesive or adhesive interactions. If multiple layers are there, how the cohesive forces are going to come into the picture, and adhesive nature. Suppose if their surface roughness is different, then definitely their adhesion property is different. That can be still studied using this nano mechanical characterization. And how you are going to do the same analysis. How much force you apply, how much depth of penetration, where the kinks are. You can see here, the kink is there. That means there is a delamination is happening. Here this says that this delamination is happening here, which you can still further go into understand how you can modify that adhesiveness. You do some chemical treatment or do some betterment. So you come up here again, you see, yes, now it's okay. Like that. I hope with this, I try to convince you that it's very essential to understand the properties at the nanoscale. And by this particular nano indentation technique or nano mechanical characterization, many techniques were there, but I just pin focusedly one or two techniques on this set, but many are there. So with them, you can really understand how you are going to understand the hardness of this material, plastic nature, heat nature, yield strength. So many things are there. I didn't even speak about them, but still many things are there to be covered. So using nano indentation, these many things can be done. Of course, using nano scratch also, you can understand elastic plastic nature, cohesive adhesive, bond strengths, many things you can study. With this, I close my session. Thanks for giving this opportunity.
Thank you very much, sir. And this is the time for questions. If you have any questions, please come forward. I think no questions. So the overview, sir, has started the mechanical response in materials. Started with that, the difference between the rubber band and steel. And nano side, the mobile screen glass may erode the interest in the students and learners. That's one thing. And they mentioned about distribution of stress in different scales and different phases is one thing. And also introduce the piezo response force microscopy to test the sample is one. And the overview on the nano indentation, nano scratch is really good to know the mechanical properties at nano scale. So by this, we are going to close this day, and the next session will be the tomorrow morning, 10 o'clock. So we'll all meet in the tomorrow, 10 o'clock. Thank you very much for your, thank you very much. Thank you so much.